Somewhere in the vast and silent wilderness of the cosmos, a star is committing a slow, celestial murder. It's not doing this out of rage or rivalry. It's following the cold laws of physics, in a dance older than our planet, but far more violent than any natural act we know. The star is known to astronomers as a Black Widow Pulsar, and like its arachnid namesake, it survives by slowly devouring its partner. It tears at it bit by bit with torrents of high-energy radiation, robbing it of mass and future, until what's left is a ghost of a once thriving star. These strange and sinister objects lie among the most enigmatic puzzles in space, unfolding mysteries that even the most powerful telescopes struggle to unravel. In today's journey through the cosmos, we dive into a realm of deadly stellar cannibalism, extreme physics, and questions so baffling, they challenge our understanding of what it means to be a star, or even to survive in this hostile universe. But before we continue, subscribe to the channel so you don't miss out on any of these videos. To understand Black Widow Pulsars, we need to peel back several layers of astrophysical evolution. First, we must explore what a pulsar is, and how something so tiny, so seemingly insignificant in size, only about 20 kilometers across, can emit more energy than a million suns. A pulsar is a type of neutron star, the ultra-dense remnant of a massive star that has exploded in a supernova. After the core collapses, what remains is a city-sized ball of neutrons, packed so tightly that a single teaspoon of its matter would weigh billions of tons. But not all neutron stars are created equal. Some rotate with extraordinary speed, hundreds of times per second, and emit beams of electromagnetic radiation from their magnetic poles. These are pulsars, and if their beam happens to sweep across Earth, we detect it like a cosmic lighthouse flickering with clockwork precision. Among pulsars, the Black Widow variants are particularly rare and deadly. They fall into a subclass known as millisecond pulsars, which spin with incredible velocity, up to 700 times per second. That's faster than a kitchen blender. But the most chilling feature of a Black Widow pulsar is its companion, usually a small, low-mass star, often just a fraction the size of our Sun caught in a tight, brutal orbit. This companion is being stripped apart. As the pulsar spins, it bombards its partner with a relentless onslaught of gamma rays and high-energy particles, blasting away its outer layers. Over time, the companion is reduced to a planetary husk, or in some cases, disappears entirely. It's a relationship defined not by balance, but by annihilation. The first Black Widow pulsar ever discovered, PSRB 1957+20, stunned the astronomical community when it was found in 1988. This object spins 622 times per second and orbits a companion that has already been reduced to about 0.02 solar masses, barely more than Jupiter. Even stranger, the system lies about 6,500 light-years from Earth in the constellation Vulpecula. It moves at a blistering pace, zipping through the galaxy at around 1,000,000 kilometers per hour. In a way, it's a wandering death machine, small, fast, and violent. Observations showed that the companion was surrounded by a comet-like tail of gas, evidence of the relentless bombardment it suffers. With every second, the pulsar consumes more of its mate, like a Black Widow spider killing its partner after mating. Hence the grim nickname. But why do these systems form in the first place? And why are they so rare? To answer that, we must travel billions of years back in time, to the moment when the original massive star first exploded. After the supernova, the neutron star is born. Initially, it's not spinning very fast. But if it is in a binary system, it begins to steal matter from its companion, drawing in gas and angular momentum. This process, called accretion, spins the neutron star up over millions of years. Essentially, it gets recycled, reaching millisecond spin rates. Ironically, it's this very act of theft, of absorbing its companion's matter, that both powers the pulsar and seals the companion's doom. The more it feeds, the faster it spins, and the deadlier it becomes. It's a vampire star that kills to stay young. Some theories suggest that Black Widow pulsars might represent a transitional stage in stellar evolution, showing us how binary stars can evolve into solitary pulsars. In other words, this cannibalism might be how some of the isolated millisecond pulsars we observe today came to be. Their companions are simply gone, vaporized into interstellar dust. Others hint that these systems may even give rise to exotic remnants, like planetary mass cores or ultralight brown dwarfs. There's also the possibility that some of these systems are hiding something deeper, dark matter interactions, or even conditions that could test the limits of general relativity in extreme environments. The story doesn't end with the Black Widows. There's a related class of objects known as Redback Pulsars, named after a cousin of the Black Widow spider. These systems have slightly larger companions, usually around 0.2 solar masses, and the interaction is even more complex. In some Redbacks, the companion isn't just being eroded, it's actively feeding the pulsar in a bizarre cycle of mass transfer and magnetic fury. Observations using X-ray and radio telescopes show that these systems can switch states, flickering between accretion-powered X-ray emission and radio pulsar mode. This dual personality suggests that these systems may alternate between devouring and pausing, like a predator toying with its prey. It's one of the few known cases in astrophysics where an object can effectively change its entire identity. The deeper we look into Black Widow systems, the stranger the universe becomes. In some cases, the pulsar's intense radiation is so powerful that it actually blows a hole in the companion's atmosphere, literally evaporating it into space. These outflows form plasma clouds that can obscure or distort the pulsar's signal. From Earth, this creates strange radio eclipses, flickering gaps in the pulsar's emission that vary over time. By studying these eclipses, scientists can map the geometry of the outflow, like peering into the crime scene of a slow-motion stellar murder. But there are still unresolved mysteries. For instance, why do some companions seem to survive the onslaught, while others vanish completely? Could there be stabilizing mechanisms at play, magnetic fields, orbital changes, or even unknown types of stellar matter? Another question lies in their distribution. Black Widow pulsars are extremely rare, yet they seem to appear more often in certain environments, like globular clusters, dense collections of old stars. These clusters provide the perfect gravitational theater for close encounters and binary pairings, but they also add noise to the analysis. Could interactions with other stars or remnants in the cluster accelerate or hinder the pulsar's deadly dance? There's also the philosophical unease these systems provoke. A star, by every definition we have, is supposed to be a beacon of light, a giver of life. Yet, in this case, we have stars that destroy, relentlessly, surgically, with no reprieve. They are death engines, weaponized by physics, operating on a scale that dwarfs any human war or catastrophe. The idea that nature not only permits such violence but depends on it for certain evolutionary outcomes is both chilling and awe-inspiring. In a way, Black Widow pulsars remind us that survival in the universe isn't gentle. It's a process of domination, of outlasting, of absorption. And what happens when this process reaches its end? If the companion is completely destroyed, the pulsar may continue spinning for billions of years, gradually slowing as it emits radiation. In the cold emptiness of space, it becomes a silent relic, still pulsing, but forever alone. These solitary millisecond pulsars are some of the most stable clocks in the universe, with timing precision rivaling atomic timepieces on Earth. Ironically, after all that violence, they become symbols of cosmic order. They're even used in pulsar timing arrays to search for gravitational waves, ripples in spacetime caused by the collisions of supermassive black holes. So in a bizarre twist, these killers may one day help us detect the most subtle distortions in the fabric of reality itself. Some Black Widow pulsars don't just kill, they linger near the brink of absurdity. Take the system PSR J1311-3430, discovered in 2012. This one pushes the limits of what we thought was possible. The pulsar spins at nearly 2.5 milliseconds per rotation and orbits its companion every 93 minutes, the shortest known orbital period for any pulsar binary system at the time of its discovery. That's shorter than the runtime of most movies. And the companion? Just 0.008 times the mass of the Sun, barely more than a large gas giant, yet still recognizable as a star-like object. In a few million years, it might not exist at all. It's currently being peeled apart by relentless winds of radiation and particles. Observations show that it's so close to the pulsar that it's tidally locked, with one side being scorched constantly. The other remains in a kind of eternal night. The extremes of hot and cold on that tiny orb must be beyond imagination. And the mechanism by which this stripping occurs isn't just brute radiation, it's angular momentum. As the pulsar spins, it spews out high-energy winds, and as those winds interact with the weaker magnetic field and loosely bound material of the companion, they generate drag. This drag saps energy from the companion's orbit, creating a death spiral. The closer it gets, the faster it loses mass. And in many cases, this process is visible to us. Telescopes like Fermi Gamma Ray Space Telescope, Chandra X-ray Observatory, and Green Bank Telescope have observed the scorching in various spectra, from gamma rays to radio waves. These instruments revealed tales of ionized gas, thermal flares, and strange, periodic dimming in the signals, like an SOS from the doomed companion. These signals are more than just data, they are stories. Each wobble in the signal tells of a moment of atmospheric stripping. Each irregularity in the orbit speaks to a new instability in the system. Over time, by monitoring hundreds of such events, astronomers can build a timeline of the companion's death. Some have tried to simulate this process in computer models, building three-dimensional visualizations of how the matter is peeled off, blown outward, and eventually dissipates into the interstellar medium. These simulations show twisted trails of hot plasma, bent by gravitational forces and distorted by magnetic fields, like fiery ribbons unraveling in zero gravity. But here's where the mystery deepens. Some companions, thought to be on the verge of complete obliteration, suddenly show signs of activity, flickering with pulses of infrared light or changing their light curve in subtle ways. This raises questions. Are these stars adapting? Are they somehow stabilizing, building up resistances, or even regaining mass through unknown means? Some models suggest that magnetic feedback loops could momentarily shield them, buying more time before the inevitable end. Others propose that the companion's core becomes denser and more resistant as the outer layers are lost, creating a kind of rocky remnant that might endure long after its gaseous envelope is gone. Could we be witnessing the birth of a new class of celestial object, a planetary-scale corpse of a star? Intriguingly, the aftermath of such annihilations may leave behind more than an isolated pulsar. It may also leave circumpulsar debris disks, potentially composed of the material stripped from the companion. These dusty, tenuous rings could one day cool and coagulate into exotic planetary bodies. In fact, there is indirect evidence of pulsars with planets orbiting them, a discovery that stunned astronomers in the early 1990s. The first exoplanets ever detected were actually found around a pulsar, PSR B1257+12. These planets are unlike anything in our solar system, formed not in the gentle womb of a protoplanetary disk but in the aftermath of stellar death and violent rebirth. Some speculate they could be the end product of a Black Widow system, the remnants of a once-living star, reforged into rocky orbs by gravity and time. The full population of Black Widow pulsars is still unknown. Detection is notoriously difficult. Many are found by accident, as part of wide-field pulsar surveys, or by unusual gamma-ray emissions that don't quite match expectations. Some may be hiding behind veils of plasma blown from their companions, making their signals intermittent or hard to interpret. Others may be in such tight orbits that Doppler effects warp their pulse timing beyond our current models. To find them, researchers are now turning to advanced algorithms, machine learning, and data from telescopes like FAST in China and the upcoming Square Kilometer Array, SKA. These facilities promise to multiply our detection capabilities, and perhaps reveal hundreds more Black Widow systems, each one a ticking time bomb in the night sky. Yet even if we find more, there's the haunting realization that many Black Widow pulsars may already be finished, their companions vaporized, their systems now silent. These lone pulsars, spinning with eerie precision, are like survivors of forgotten wars. We see only the outcome, not the violence that led to it. And it forces us to wonder, how many stories of annihilation play out in the cosmos with no witness? Some researchers believe these systems could be used as laboratories for extreme physics. Their conditions are impossible to replicate on Earth, with magnetic fields trillions of times stronger than anything we can generate, and gravitational environments where even light curves under pressure. By analyzing their timing, their spin-down rates, their spectra, and the behavior of their companions, we can test aspects of general relativity, nuclear matter equations of state, and even quantum field effects in curved spacetime. In other words, these destructive stars might be our best shot at understanding some of the universe's deepest secrets. And yet, beyond the science lies the aesthetic of cosmic tragedy. The idea of a star living in orbit with a monster that will eventually consume it, knowing there's no escape, is both horrifying and poetic. It makes us reflect on our own place in the universe, how delicate balance can give way to annihilation, how survival often comes at a cost. These systems challenge the notion that the universe is neutral. In some sense, it feels personal, violent, real, alive. Many have speculated whether Black Widow Pulsars could ever be relevant to life-bearing worlds. Could such a system, in some incredibly rare configuration, host a planet in a stable orbit? The radiation alone would make life as we know it impossible. But in the realm of astrobiology, the extreme often invites the imagination. What if, nestled behind a dense shield of magnetized plasma or orbiting at a safe distance, a rogue world caught in the same gravitational web managed to persist? What if complex chemistry emerged under the umbrella of a pulsar's consistent timing? Unlikely, yes. But the history of space discovery has taught us to never say never. In the coming decades, as we deploy more sensitive detectors and more powerful surveys, we'll likely uncover more of these systems. Each one will tell its own version of the same cruel narrative, a star eating its partner to sustain its spin. And each will force us to ask the same uncomfortable question: is survival, at its core, a violent act? As we gaze into the depths of the cosmos, seeking beauty and answers, we must also face the dark truths it holds. Not every star is a source of light and hope. Some are executioners. Some write their stories in silence, spinning endlessly in the void, their beams slicing through the galaxy like warnings etched in radio waves. There is something haunting about the idea of a star whose very heartbeat, the rhythmic pulses of radiation we receive across the electromagnetic spectrum, is powered by destruction. The Black Widow Pulsar, elegant in its precision and terrifying in its intent, has become a symbol of nature's duality, beauty and brutality, order and chaos, life and annihilation. But the mystery surrounding them doesn't end with what they are. It extends into the realms of why they exist at all, and what role they play in the grand evolutionary mechanics of the cosmos. To grasp this, we must understand the evolutionary sequence that leads to the formation of such a system. It begins with a binary pair, two ordinary stars orbiting one another. As time progresses, the more massive star exhausts its fuel and explodes in a supernova, becoming a neutron star. But the story doesn't end with the explosion. If the binary system survives the violent kick of the supernova, the neutron star begins to draw matter from its companion. This process of mass accretion spins up the neutron star, compressing decades of stellar feeding into a few million years of rapid rotation. At some point, the neutron star becomes so efficient at converting this infalling matter into angular momentum that it crosses the threshold into becoming a millisecond pulsar. From that moment, it begins to radiate ferociously. Now imagine the companion, once a thriving star, now a victim of tidal locking, gravitational decay, and relentless energy bombardment. The energy flux from the pulsar irradiates its near side so heavily that it begins to puff out and boil off gas into space. This creates an extended atmosphere or wind that enshrouds the entire system, partially or completely obscuring the pulsar at certain viewing angles. Some of these eclipses are not just passive dimming events, they're interactive. The pulsar's emission interacts with the wind, generating shocks, accelerating particles, and sometimes lighting up the environment in X-rays and gamma rays. These shock fronts, traveling at near-relativistic speeds, offer real-time windows into how energy is transferred in these deadly partnerships. What's even more fascinating is how these systems allow us to observe real-time orbital evolution. By timing the pulses of the neutron star down to the microsecond, astronomers can detect minute changes in the orbital period of the binary system. These changes often confirm that the orbit is shrinking, not through some dramatic collision, but through gradual loss of angular momentum. This is evidence that gravitational waves, those elusive ripples in spacetime first predicted by Einstein, are being emitted by these systems. Though weaker than those generated by the merger of black holes or neutron stars, the consistent, measurable gravitational wave signatures from pulsar binaries provide yet another avenue of astrophysical investigation. In fact, pulsar timing arrays, networks of precisely timed pulsars, are one of the most promising tools for detecting ultra-low-frequency gravitational waves. Black Widow pulsars, given their rapid rotation and high stability, despite their violent nature, are ideal contributors to these arrays. So paradoxically, these destroyers of stars may help us detect phenomena from the furthest reaches of the universe, mergers of supermassive black holes in distant galaxies, relic gravitational waves from the early universe, or even dark matter clumps perturbing space on cosmic scales. And speaking of dark matter, there's an intriguing fringe hypothesis that Black Widow pulsars might serve as indirect probes of it. Because of their extreme gravitational and magnetic environments, these systems could potentially capture or interact with exotic particles theorized to comprise dark matter, such as axions or weakly interacting massive particles, WIMPs. If such interactions occur, they might subtly affect the pulsar's spin rate, emission pattern, or orbital dynamics. We don't yet have concrete evidence of this happening, but Black Widow systems are under intense scrutiny for any deviations from expected behavior, because in such systems, even a small anomaly might be a window into new physics. Meanwhile, we've also begun considering their role in galactic archaeology. Because millisecond pulsars can survive for billions of years, they act like fossil clocks. By mapping their positions, velocities, and orbits through the Milky Way, we can reconstruct the history of stellar populations, gravitational perturbations, and even the distribution of mass in the galaxy. Black Widow pulsars, though few in number, add high-velocity data points to these models. Many are runaway systems, moving at speeds that suggest they've been ejected from dense environments like globular clusters or the galactic core. Some even follow hyperbolic orbits, hinting that their past may involve interactions with supermassive black holes or massive star-forming regions. Each system's trajectory is like a forensic trail, pointing back to a violent origin. And there's another strange possibility. Could these systems be precursors to something even more exotic? In theory, as the companion is stripped to near-nothingness, the remaining remnant could collapse into a strange quark star or even something more speculative, like a preon star, a hypothetical object composed of subquark particles. Though still purely theoretical, these ideas push the boundaries of what matter can be under such intense pressures. Black Widow systems may be the final stages before nature flips into a new regime of physics, one not yet observed or confirmed. From a technological perspective, the study of Black Widow pulsars is pushing our instruments to new levels of precision. The detection of such small, distant, and faint signals requires incredibly sensitive radio telescopes, data pipelines that can filter petabytes of noise, and software that can model relativistic effects with exquisite accuracy. AI and machine learning are now being used to identify pulsar candidates that might have previously gone unnoticed. In some cases, computers are finding new Black Widow candidates buried in archival data from a decade or more ago, data that was once deemed inconclusive. This raises the question, how many more of these systems are out there, quietly cannibalizing companions in the darkness? And with that comes a terrifying thought. If a Black Widow pulsar formed near Earth, or worse, if a system like that somehow came drifting into our stellar neighborhood, what would it mean for us? Thankfully, the odds are infinitesimal, but it's worth considering. The radiation alone would sterilize life across any planets within light years. If close enough, the gravitational interactions could distort planetary orbits, destabilize the Oort cloud, and trigger cometary bombardments. Even from a safe distance, the gamma-ray pulses could interfere with satellite communications, disrupt atmospheres, and damage electronics. It would be, in every sense, a cosmic predator, beautiful to observe from afar, but devastating up close. Despite their danger, Black Widow pulsars also embody hope. Not in the traditional sense, but in the sense that they demonstrate how far human curiosity can reach. They are invisible to the naked eye, yet we know they exist. We can map them, model them, predict their behavior, and use them to test the deepest theories of physics. This ability, to extract meaning from faint pulses in the void, is uniquely human. We've taken what was once noise in the sky and turned it into knowledge, into narrative, into awe. As our technological gaze sharpens, we may one day watch the final moments of a Black Widow system in real time. We may witness the last flicker of light from a dying companion, the final surge of radiation, the last pulse before silence. And when we do, it will be not just an ending, but a beginning, a moment where death in the stars becomes insight for those watching from a small blue dot far, far away. The philosophical implications of Black Widow Pulsars deepen the more we observe them. These cosmic executioners challenge our traditional narratives about binary star systems, about companionship in the universe. In most stellar pairs, the stars evolve together, sometimes gracefully, sometimes violently, but there's a shared destiny. In contrast, the Black Widow narrative is a betrayal. One partner grows stronger by systematically obliterating the other. It's not mutual destruction, it's parasitic. And yet, this asymmetric evolution may be far more common in the universe than we once believed. From a narrative perspective, this is the universe at its most gothic, a vampiric star, spinning in eternal night, siphoning the life from a fading companion until there's nothing left but silence and memory. We assign metaphors and human emotions to these objects not because they possess them, but because it's the only way we can begin to internalize such extremes. Just like we call them widows, we impose familiar roles upon the unfamiliar. The cosmos doesn't love, doesn't grieve, doesn't mourn. But we do. So when we see a star die so another may live, we imagine desperation, violence, sacrifice. The Black Widow Pulsar is not merely an astrophysical curiosity. It is a cosmic archetype, an entity that reveals how survival can hinge upon the complete unraveling of another. This phenomenon isn't just something we detect, it's something we feel in the deep psychological recesses of our species, resonating with our own stories of consumption, dependency, and loss. Yet, in that same mechanism of destruction lies the seed of something constructive: timing precision. The incredible regularity of millisecond pulsars, often accurate to within a few nanoseconds, makes them more than just astronomical wonders. They are natural timekeepers, clocks forged in cosmic crucibles. For decades now, astronomers have been studying these precise pulses to understand not just the pulsars themselves, but also the fabric of spacetime. In this sense, the Black Widow Pulsar becomes a tool, not just for understanding the stars, but for mapping gravitational phenomena that span billions of light years. Here's how: when a pulsar's signal is affected by a passing gravitational wave, even slightly, it alters the timing of that pulse. By measuring the discrepancies from many different pulsars simultaneously, we can triangulate the presence of these ripples in spacetime. This is the principle behind pulsar timing arrays (PDAs) and the Black Widow Pulsars, with their unusually sharp, fast pulses, are among the best candidates to use in such arrays. Each pulse is a data point in a galactic scale experiment, with the Earth at the center of a web of spinning neutron stars. The beauty of this is staggering: a dead star, spinning impossibly fast after cannibalizing its partner, is now a beacon to measure the breathing of the universe itself. Every flicker of its light across the galaxy is another stroke in the painting of a gravitational map we're only just beginning to perceive. We aren't just watching stars die, we're watching the skeleton of the cosmos reveal itself in real time. Even more astonishing are the possibilities presented by a subclass of systems called Redbacks, which are closely related to Black Widow Pulsars. The distinction lies mostly in the mass of the companion. Redbacks have more massive companions, usually 0.2 to 0.4 solar masses, and are thought to be in an earlier stage of the same death spiral. Some Redback systems may even flip between being accretion-powered X-ray binaries and rotation-powered radio pulsars, a phenomenon known as a transitional millisecond pulsar. These transitions are rare, but they offer priceless insights. Imagine witnessing, in real time, a system shift from feeding to spinning, from devouring mass to emitting pulses. Observing this switch offers a glimpse into the moments when a neutron star awakens as a millisecond pulsar. It's like catching the second a cocoon breaks open, except the butterfly is made of degenerate matter, and the wings are beams of radiation that slice across the cosmos. One of the most intriguing transitional pulsars known is PSR J1023+0038. Originally discovered as a radio pulsar, it mysteriously shut off and then reappeared with accretion activity. The transformation, happening over just a few years, was marked by the reappearance of an accretion disk and dramatic changes in its X-ray emission. In that brief cosmic heartbeat, we observed the delicate dance between two stellar states, a momentary stutter in an otherwise steady rhythm. These transitional systems could hold the key to understanding the full life cycle of pulsars, bridging the gap between X-ray binaries and isolated millisecond pulsars. But transitional systems also stir deeper questions. Are all Black Widow pulsars fated to undergo such a phase? Do they oscillate unpredictably between devouring and radiating? Is there a limit to how much spin they can acquire before something fundamental in their structure collapses or changes? Theoretically, neutron stars have a maximum rotation rate, the breakup speed, beyond which centrifugal forces would tear them apart. Current models suggest this limit is around 0.5 milliseconds per rotation. The fastest known pulsar, PSR J1748-2446 AD, rotates at 1.39 milliseconds. Black Widow pulsars like PSR B1957+20 are pushing close to that threshold. Could there be pulsars out there spinning even faster, just beneath our detection limits? If so, they might teach us about the upper bound of matter's cohesion, or hint at even stranger forms of dense matter, like quark-gluon plasmas or color superconductors, states of matter that remain purely theoretical, trapped in the equations of quantum chromodynamics. In this way, Black Widow pulsars aren't just graveyards of dying stars. They're laboratories. They're particle accelerators powered by gravity and time. They're clocks. They're killers. And they're mysteries. And still, questions abound. Could the stripped-down remnant of a companion evolve into a planet-sized object, orbiting a pulsar forever in a ghostly dance? Some researchers think so. The idea of pulsar planets has been floated for decades now, and while rare, it's not impossible. These would be planets forged in fire, tempered by radiation, and possibly composed of exotic matter. The very existence of such an object would defy most planetary formation models, suggesting that the aftermath of stellar death might not be an end, but a kind of rebirth. Even more speculative theories propose that the remnants of these systems could eventually cool and stabilize into long-lived remnants, perhaps even detectable as rogue planets or dense, inert stellar cores wandering the interstellar medium. Could such relics be captured by other stars, injecting complexity into otherwise stable planetary systems? Could they act as delivery mechanisms for heavy elements, magnetic flux, or gravitational instabilities? We simply don't know yet. What we do know is that our journey to understand Black Widow pulsars has only just begun. Every new detection refines our models, and every unanswered question adds another layer to the enigma. As we push deeper into space with instruments like the James Webb Space Telescope, SKA, and Athena X-ray Observatory, we'll inevitably uncover more of these violent systems. Some will fit neatly into our expectations. Others will shatter them. And when the next signal comes in, a regular pulse, steady and sharp from the void, we'll listen not just for its beat, but for the story it tells. Because in that beat lies not just the physics of a dying star, but the poetry of a universe that creates, destroys, and reveals itself in whispers of light. But even as we dig deeper into the astrophysics, one truth about Black Widow pulsars stands unshaken. They represent one of the most precise, violent, and paradoxical mechanisms in the known universe. These stellar reapers offer an unprecedented union of raw destructive power and impeccable timing accuracy. A single Black Widow pulsar can outshine entire stars in radio wavelengths, vaporize its companion atom by atom, and still behave with the timing regularity of the best atomic clocks ever built by humankind. This contradiction is not merely poetic, it's fundamental. It teaches us that order and chaos aren't always opposites. In the case of Black Widow Pulsars, they are partners, locked in a celestial embrace. What deepens the mystery further is the realization that the number of known Black Widow systems may only scratch the surface. Astronomers have catalogued just a few dozen of these systems, but the real number could be in the hundreds or thousands. The reason for this underrepresentation isn't because they're rare, but because they're elusive. The winds from the evaporating companion often cloak the pulsar's radio signal, leading to long-term eclipses and signal distortions. These factors make them difficult to detect using traditional pulsar surveys. Only through persistent observation, creative signal processing, and sometimes pure luck have we been able to uncover the few we know. This cloak of obscurity makes them cosmic ninjas, hidden, fast, deadly, and incredibly efficient. For astronomers, each new detection is like lifting the veil on a new kind of star death, one that doesn't explode outward like a supernova, but instead collapses inward through erosion and decay. It's a slow-motion supernova played out over millions of years, with a neutron star as the villain and a shrinking, terrified companion as the victim. Still, the neutron star itself, while central to the system, is not unchanged by the drama. Black Widow pulsars can accumulate angular momentum to a point where their structure and shape are permanently altered. The centrifugal forces at such high spin rates flatten the star into an oblate spheroid, making its equator bulge outward by several kilometers compared to its poles. This distortion could subtly affect its magnetic field, radiation pattern, and even the shape of the beam that reaches Earth. Such effects are small but measurable, and they can offer clues about the internal composition of neutron stars, something still largely mysterious. What lies inside a neutron star? Theories range from neutron superfluids to hyperons, to the aforementioned strange quark matter. But confirming any of these possibilities requires extreme precision in mass and radius measurements, something only a select group of pulsars can offer. Black Widow pulsars, by virtue of their violent environments and tight orbits, provide unique testing grounds for such measurements. For example, the timing delays caused by the companion's atmosphere can be used to probe the relativistic effects predicted by general relativity. The stronger the delay, the more compact the neutron star is likely to be. Over time, accumulating enough data across many systems could begin to close the gap on one of astrophysics' longest-standing questions: what exactly is the equation of state for ultra-dense matter? And it doesn't stop there. As the field of multi-messenger astronomy grows, so too does our ability to observe these systems in more than just one wavelength or signal type. We now observe Black Widow pulsars in radio, X-ray, and gamma ray, and soon we may observe them through gravitational waves or neutrino bursts, particularly during sudden structural events like starquakes or crust cracking. Each of these observation channels provides a different lens through which to view the same celestial phenomenon. Radio waves give us precise timing, X-rays and gamma rays show us the energy flux and shock fronts, gravitational waves might reveal changes in orbital dynamics, and neutrinos, if we ever detect them from such a system, could offer a window directly into the star's core. This convergence of signals, data, and theory is transforming how we do science. For example, the Fermi Gamma Ray Space Telescope has found pulsars that were invisible to radio surveys, suggesting that we may be missing a whole population of gamma-ray loud, radio-quiet Black Widow pulsars. Some might even lie hidden behind dense interstellar clouds or inside globular clusters where signals scatter or become jumbled. With future missions like the Cherenkov Telescope Array and Rosetta, we'll likely find many more, each adding another data point to the growing constellation of deadly cosmic clocks. Now consider this. If Black Widow pulsars can tell us so much about the structure of neutron stars, the mechanics of relativistic binaries, and even the broader dynamics of the Milky Way, could they also be used as a navigation system? The answer is absolutely. Scientists have already proposed using millisecond pulsars as the basis for an interstellar GPS system. Because their timing is so precise and their locations are well known, a spacecraft equipped with a pulsar receiver could triangulate its position anywhere in the galaxy. It's a form of deep space navigation that doesn't rely on Earth-based communication. This concept, known as XNAV, X-ray navigation, is currently being tested in simulations and could eventually guide spacecraft to distant planets, moons, or even other stars. Imagine that. A star which murdered its partner could one day be a guidepost for human exploration. A predator becoming a pathfinder. In that single conceptual reversal lies perhaps the greatest metaphor of all, one where even death, destruction, and loss can be repurposed into tools for understanding, discovery, and hope. Black Widow Pulsars challenge us not just to expand our science, but to evolve our thinking. They're not merely end states. They are active processes, engines of change and catalysts of inquiry. They push the boundaries of what matter can endure, what light can reveal, and what gravity can teach. Their very existence forces us to reckon with extremes, not just in temperature, density, or velocity, but in meaning. Because when we look into the heart of a Black Widow pulsar, we are seeing a cosmic mechanism so unflinching in its violence, and yet so precise in its message that it becomes something more than just an astronomical object. It becomes a symbol of the universe's indifference, and of our refusal to look away. As we prepare for the next generation of telescopes and detectors, massive observatories perched on mountaintops, orbital platforms humming through the void, and perhaps even autonomous probes venturing into interstellar space, we will carry with us the signatures of these dark stars. Their pulses, their rhythms, their warnings. And when we detect that next peculiar dip in signal, or that oddly shifting gamma ray profile, we might just be peering at a new Black Widow pulsar, still hidden in the fabric of the universe, still devouring, still whispering secrets we've yet to decode. We will listen. We will understand, not all at once, but piece by piece, pulse by pulse. Each new Black Widow pulsar is like a line of cosmic code waiting to be deciphered. With every rotation, it offers a tiny sliver of the universe's instruction manual, written not in ink but in radio waves, gamma rays, and gravitation. These signals reach across time and space to paint a clearer picture of the rules that govern matter, energy, and death. But there's more. The implications of these systems don't stop at pure science. They also challenge our assumptions about how life might arise, survive, or be obliterated elsewhere in the cosmos. Consider the environment near a Black Widow pulsar: constant bombardment of high-energy radiation, wildly shifting gravitational fields, and matter being torn apart and accelerated to relativistic speeds. It is, by all accounts, an inferno, a place of pure destruction. And yet, in their extremes, they help define the limits of habitability. By understanding what destroys planets and atmospheres, we also better understand what protects them. Studying these deadly stars gives us more refined models for planetary shielding, magnetospheres, and atmospheric loss. For exoplanet researchers, Black Widow systems act like stress tests written by nature, torture chambers that illustrate the worst possible scenarios for planetary systems. The insights gained may one day help us evaluate whether a distant Earth-like world could actually remain stable long enough to support life. In addition, there's a curious anthropocentric truth here. The very signals that destroy in their immediate environment are the same signals we use to detect, study, and navigate. This dual nature, a beam that both erases and reveals, is among the most poetic characteristics of Black Widow pulsars. They are destroyers and informers, beacons and blacksmiths. They forge understanding through annihilation. In recent years, artificial intelligence and machine learning have begun playing a greater role in identifying and analyzing these elusive systems. The data collected from sky surveys is vast, far too vast for human astronomers to comb through efficiently. But neural networks trained on pulsar data can identify subtle patterns that elude even expert eyes. They have uncovered dozens of new pulsars and will likely discover hundreds more. It's possible that in some server rack, humming away unnoticed, lies the next great Black Widow discovery, waiting to be surfaced by an algorithm designed to see the unseen. But algorithms, for all their sophistication, still rely on humans to ask the right questions. What makes a Black Widow? How do we define the edge between a Redback and a true widow? What determines whether the companion is consumed entirely or left as a planetary corpse? These questions remain unresolved and require not only computational models, but observational evidence from a global network of telescopes. Radio arrays like FAST in China, Meerkat in South Africa, LOFAR in Europe, and the upcoming Square Kilometer Array that will become the largest and most sensitive radio observatory ever constructed. As our tools grow more powerful, our reach extends further into the galactic disk and even into globular clusters, ancient stellar cities packed with tightly bound stars, where gravitational interactions make binary and millisecond pulsars more likely to form. Some of the most exotic Black Widow systems may be hiding there, cloaked in layers of gravitational noise and background interference. One such environment, Terzan 5, has already yielded fascinating pulsars. It's likely that many more remain buried, waiting for detection. Even now, as you listen to this, pulses from a Black Widow pulsar are washing over Earth. They've been traveling for thousands, sometimes tens of thousands of years. They left their origin long before the first cities rose on this planet, before the pyramids, before writing, before fire was controlled by our species. And only now are they reaching us, whispering of a violent dance that played out in some distant pocket of the galaxy, long ago. These signals are time capsules, carrying with them the aftermath of stellar betrayal, encoded in beats no wider than a human heartbeat. It's awe-inspiring to realize that our brief human lifespans intersect with these messages only momentarily. We are here, blinking into the cosmos, trying to understand what it means that a neutron star spins 600 times per second and vaporizes its only companion in a process lasting millions of years. And in that effort, limited, frail, mortal, we have reached deep into the mystery of time, density, and fate. There are also tantalizing links between these systems and other astrophysical phenomena. Could some isolated neutron stars we see today have once been Black Widow systems that finished their consumption and were left to spin alone, undisturbed, emitting silent radiation until they fade into blackness? Could they represent a post-widowhood phase of evolution, ghosts of systems that once throbbed with violence but now pulse in solitude? Even more extreme, could these systems, under the right conditions, collapse into something else entirely? A Black Widow pulsar that grows too massive might pass the Tolman, Oppenheimer, Volkoff limit, the maximum mass a neutron star can possess before collapsing into a black hole. If so, we might have yet another channel through which black holes can form, not through supernova explosions, but through slow, patient consumption. This would create a cosmic irony, a star that devours its partner only to eventually consume itself. And if these transitions can happen, they might produce unique gravitational wave signatures. Unlike black hole mergers or neutron star collisions, this would be a more gradual process, subtle distortions over long timescales, detectable only with extreme precision. But if found, they could fill in a critical missing piece of astrophysical evolution, connecting stellar deaths to the dark hearts of galaxies. The science is stunning. The stories are staggering. But the greatest mystery of all might be this: how many Black Widow pulsars are still hiding from us, ticking away in distant starfields, unseen and unfelt, waiting for a civilization advanced enough to hear them? Every time we turn our eyes and ears to the sky, we come a little closer to answering that. And so we keep watching. We keep listening. Because the stars are still speaking. And the stars are speaking in riddles. Among these riddles, the Black Widow pulsars occupy a particularly enigmatic space. They are not simply anomalies. They are clues. Clues to a universe far more dynamic, brutal, and rich with extremes than we can comfortably imagine. Every rotation, every pulse, every tiny delay in their signal timing carries embedded truths about gravity, matter, and time itself. Some of those truths are purely scientific, measurable and repeatable. But others drift into the philosophical, where the implications stretch beyond data. What does it mean that a star can be both one of the oldest relics in the galaxy and one of the fastest spinning objects in existence? What does it say about the nature of existence when we observe an object so precise it rivals our atomic clocks, and yet so violent it peels its companion apart molecule by molecule? These aren't just questions for astronomers. They are questions for humanity. Because Black Widow pulsars are, at their core, about relationships warped by gravity, betrayal, and survival. A pulsar doesn't exist in a vacuum, metaphorically, even if physically it often does. Its very identity as a Black Widow depends on its interaction with another. It is the act of consumption, of transformation to violence, that gives it this title. And in studying that act, we are invited to confront the nature of dependency in extreme environments. How long can one object sustain the other before it becomes unsustainable? What does it look like when symbiosis turns into parasitism? And can there be redemption, any remnants of harmony, once the violence has ended? These aren't just cosmic questions. They mirror the dynamics we see in human systems, in societies, in relationships, in technology. The cosmos, for all its alien strangeness, is never truly separate from us. We're built from its ashes. We're tuned to its harmonics. When we study stars, we are also, somehow, studying ourselves. But let's return to the physics, for the Black Widow pulsars still have more to teach us. Some pulsars, particularly those in Black Widow systems, have magnetic fields that decay over time, but not always predictably. As they accrete mass and angular momentum from their companions, their fields may become distorted, compressed, or even reconfigured entirely. This results in an evolving emission profile, which astronomers track to understand the inner workings of pulsars. In essence, every Black Widow is a magnetic laboratory, demonstrating how high-energy plasmas and fields behave under conditions utterly impossible to recreate on Earth. And then there's the question of timing noise. For most millisecond pulsars, especially those used in pulsar timing arrays (PDAs), timing is nearly perfect. But Black Widow pulsars introduce a complicating factor: variability due to the companion's atmosphere. As material streams from the companion star, it creates a changing plasma cloud that can delay or refract radio pulses. This variability isn't random, it's influenced by orbital position, wind density, and solar-like activity from the companion. By carefully analyzing this noise, astronomers can reverse engineer properties of the cloud itself, its density, structure, and sometimes even its temperature. This is one of the few ways we can study atmospheres and tight binary systems without direct imaging. It's science at its most creative, using indirect clues to paint detailed pictures of unseen forces. And this noise isn't always a nuisance. In fact, it may be the key to unlocking transient events, short-lived but profound changes in the system, like sudden shifts in orbital eccentricity or dramatic changes in the rate of mass loss. Capturing one of these events in real time could offer insight into the evolution of stellar binaries under extreme pressure. It's the cosmic equivalent of catching a star in the act of transformation, an astronomical lightning strike. Some researchers believe Black Widow systems might be responsible for a portion of another mystery: fast radio bursts, FRBs. These are powerful, millisecond-long flashes of radio waves that originate from far outside the Milky Way. While many hypotheses exist, some speculate that interactions in tight binary pulsar systems, possibly involving magnetic reconnections, crust quakes, or sudden accretion events, could produce similar radio flashes. If Black Widow pulsars are even partly responsible for FRBs, they may be helping to solve not one, but two of astronomy's greatest puzzles at once. But perhaps one of the most mind-bending implications is what Black Widow pulsars suggest about the future of stellar evolution. These systems don't represent the beginning or even the middle of a star's life. They are the afterlives of stars. They are what happens after collapse, after death, after rebirth. They are the zombie systems, undead, pulsing, and still changing the cosmos around them. And in some far-off future, when the stars begin to fade and the universe grows cold, Black Widow pulsars could still remain, spinning, killing, whispering. They are survivors. Long after the sun has burned out and the Earth is gone, Black Widow pulsars will still be counting the seconds. And if somewhere, sometime, an advanced civilization still exists, maybe it too will detect the pulse of a Black Widow star and recognize it for what it is: a message, a warning, a relic, a light in the dark. Or maybe even a clock that never stops ticking. Black Widow pulsars, in their grim persistence, are clocks that tick not for the sake of timekeeping, but for the persistence of cosmic memory. They hold within their pulses the imprint of stellar generations long extinguished, keeping rhythm not with the heartbeat of life, but with the relentless machinery of decay and transformation. These stars are ancient, many billions of years old, and yet their existence today is far from passive. In fact, they are still evolving, still modifying their environments, and still challenging our understanding of what is possible at the edge of physics. Unlike ordinary stars, whose fates are relatively well charted, burn fuel, expand, collapse, or explode, Black Widow Pulsars are playing out endgame scenarios that often leave astronomers stunned and unsure where the story will end. One of the most astonishing aspects of these systems is their potential for mass transfer-induced collapse. In typical binary systems, when one star evolves and expands, it may donate mass to a nearby white dwarf, potentially triggering a nova or even a Type Ia supernova. But in a Black Widow system, the mass transfer dynamic is reversed and taken to extremes. The pulsar, once the corpse of a massive star, is reanimated by the stream of mass from its smaller companion. The more mass it steals, the more unstable it becomes. If the neutron star gains too much mass and crosses the threshold of about 2.2 solar masses, the so-called Tolman, Oppenheimer, Volkoff limit, it may suddenly collapse into a black hole. What's chilling is the stealthy nature of this transformation. It would not be accompanied by a visible supernova, no explosion lighting up the sky. The system would simply vanish. One moment, a pulsar ticking away with millisecond precision, the next silence. Radio telescopes would search for the once predictable pulses and find nothing. All that would remain might be the trajectory of a fleeing remnant, possibly a rogue planet, or the dying embers of a disintegrated companion. It is death by quiet suffocation, the kind of ending that leaves more questions than answers. Such collapses, if they occur, could contribute to the population of low-mass black holes, objects which remain strangely underrepresented in current observations. Most of the black holes we know of come from massive stellar collapses or mergers, typically well above 5 solar masses. But where are the 2 to 4 solar mass black holes we'd expect to find if neutron stars quietly collapsed under mass transfer pressure? Perhaps they are the ghosts left behind by Black Widow systems that consume too much. If so, we may one day be able to identify them not by what they are, but by what they used to be. The echoes of their former pulsar emissions might linger in the orbital movements of what they left behind, unusual binaries, planet remnants, or unexplained X-ray emissions. Future missions capable of detecting gravitational microlensing events, like the proposed Nancy Grace Roman Space Telescope, could help uncover these missing black holes. But until then, we can only infer their presence indirectly, through models, simulations, and careful statistical accounting. The idea that Black Widow pulsars might be ticking time bombs, poised to collapse into the very black holes we struggle to detect, adds a whole new layer of urgency and intrigue to their study. It transforms them from mere exotic stellar objects into crucial links in the chain of cosmic evolution, connecting the neutron star population to the elusive family of small black holes. Even more surprising is the increasing suspicion that some Black Widow pulsars may be harboring planetary systems. In 1992, the first confirmed exoplanets were discovered not around a sun-like star, but around a pulsar, PSR B1257+12. This system contains at least 3 Earth-mass planets orbiting a rapidly spinning neutron star. Though not classified as a Black Widow, it opened the door to a staggering realization: planets can and do form or survive in the most unlikely of places. Could a similar phenomenon occur in Black Widow systems? It's not just possible, it's plausible. As the pulsar ablates its companion, the material doesn't simply vanish into space. Some of it may form a disk, a thin accretion disk of plasma and gas, a torus of death and decay that encircles the neutron star. Over long periods, clumps within this disk might coalesce, giving rise to second-generation planets formed from the ashes of the star the pulsar consumed. These hypothetical planets, if they exist, would be utterly alien. Bombarded by radiation, stripped of atmospheres, orbiting within reach of the most energetic beams in the galaxy, they would not be candidates for life, but they would be invaluable laboratories. Their orbits could reveal properties of the pulsar's gravitational field, the structure of the remnant disk, and even the magnetic and relativistic interactions between the pulsar and its environment. If we ever detect such a world in a Black Widow system, it would be a planetary system built atop a funeral pyre, a reminder that even in stellar destruction, creation can follow. This idea, unsettling and beautiful, highlights one of the great paradoxes of astrophysics. The universe is a place where violence and beauty are not opposites, but partners. Stars are born in shockwaves, live through fusion fire, and die in silence or catastrophe. And from their deaths, new structures emerge, nebulae, black holes, and yes, perhaps even planets. Black Widow Pulsars embody this cycle in its most extreme form. They are the culmination of a process that begins with stellar birth and ends not in peace, but in consumption, annihilation, and the haunting persistence of a ticking corpse. As our technology improves and we deploy more sensitive detectors, especially those capable of monitoring across multiple spectra, we'll likely uncover dozens, maybe hundreds more of these systems. The Square Kilometer Array, SKA, for example, promises to revolutionize pulsar astronomy with its unprecedented sensitivity and resolution. It could detect faint pulses from Black Widow pulsars previously obscured by their own plasma clouds. It could find systems in dwarf galaxies, globular clusters, or the very outskirts of the Milky Way. And perhaps most excitingly, it could allow for real-time observation of companion evaporation, watching as these stars disappear piece by piece before our eyes. If we can measure these changes over years or decades, we may finally get a clear picture of what happens in the last phases of a Black Widow system. Does the companion shrink to planetary size? Does it implode? Does it get ejected entirely, sent hurtling through space as a rogue planet? Each scenario carries profound implications for our models of binary evolution, stellar death, and even galactic dynamics. These remnants, whether shrunken brown dwarfs or freed planets, may be wandering the galaxy in huge numbers, relics of past violence, invisible to the naked eye but leaving gravitational fingerprints in their wake. The possibility that the Milky Way is haunted by such ghosts, that countless stars now spin alone, having devoured their last companions, adds a layer of quiet melancholy to the science. These systems are, in a sense, memories. Long after the act of destruction is over, the aftermath persists. A lone pulsar, spinning silently in the darkness, is a monument to a drama no one witnessed but which shaped the structure of its region in space. Like a gravestone written in pulses, it tells us, something happened here. Something powerful. Something final. And yet, even now, it continues to pulse. A dead thing that will not stop speaking. It continues to speak not because it seeks to be heard, but because it cannot help but speak. The Black Widow Pulsar is a machine wound by death, ticking by the inertia of catastrophe, flinging out beams of radiation as it spins thousands of times per second, forever locked in a rhythm that was carved into it by the forces of destruction and transformation. It has no will, no awareness. And yet, its story unfolds in perfect precision across the cosmos, whispering clues to anyone capable of interpreting the signals. One of the most fascinating elements of these systems is their complexity. A Black Widow pulsar is not simply a rapidly spinning neutron star, it is an entire ecosystem. The ablated companion is not merely a victim, it is part of the mechanism. The clouds of ionized gas that stream from its surface don't just disappear, they create a shifting plasma environment, dense and dynamic, which surrounds the pair like a fog of chaos. This plasma absorbs, scatters, and sometimes reflects the pulsar's radio emissions, modulating the signals in ways that are both a curse and a blessing to astronomers. While this interference makes precise timing more difficult, it also provides a natural laboratory for studying how light and energy move through matter under the influence of intense magnetic and gravitational fields. This fog is not evenly distributed. It's sculpted by magnetic fields and orbital mechanics into arcs and tails, comet-like structures that stretch thousands of kilometers in the wake of the evaporating companion. These features evolve over time, responding to changes in temperature, wind pressure, and the companion's atmospheric composition. With every orbit, new patterns emerge. And within these patterns lie the keys to understanding how tightly bound binary systems operate under extremes of density, gravity, and radiation. In some cases, the evaporative process becomes unstable, leading to what astronomers call state switching. These are dramatic, sudden shifts in the pulsar's behavior, including changes in its spin-down rate, X-ray luminosity, or pulse profile. It's as if the system stumbles into a new configuration, perhaps due to a sudden change in the companion's mass loss rate or a reorganization of the magnetic field. These events are unpredictable and rare, but when they occur, they provide an invaluable glimpse into the nonlinear physics of binary evolution. Even more intriguing is the possibility that these switches could signal a more profound transformation, a phase transition in the neutron star itself. Some theorists propose that under certain conditions, the intense pressure inside a neutron star could force neutrons to decafine, forming a quark-gluon plasma. If that happens, the neutron star could undergo a sudden and irreversible collapse into a strange quark star or even a black hole. The timing and signature of such a transition would be encoded in the pulsar's pulse train, a sudden drop in spin rate, a dramatic change in luminosity, perhaps even the birth of a new class of compact object altogether. In this way, Black Widow pulsars are not just dead stars. They may be proto-strange stars, cosmic incubators for exotic forms of matter that cannot exist anywhere else in the universe. But there's more. In recent years, some of the most advanced computational models of pulsar magnetospheres have started to suggest that the emission patterns we see from these stars are only part of the story. It may be that a substantial amount of energy is being emitted not as light or radiation, but as gravitational waves. These ripples in spacetime, predicted by Einstein and confirmed by LIGO in 2015, are emitted whenever massive objects accelerate in non-symmetric ways. In the case of a pulsar with a slightly distorted shape, or a pulsar whose crust is stressed by tidal forces from a close companion, minute but detectable gravitational waves could leak from the system. Over millions of years, this energy loss could alter the orbit, slow the spin, or even catalyze collapse. Detecting such weak gravitational signals from a single pulsar is a daunting challenge. But the ongoing effort to construct a galactic-scale gravitational wave detector using a pulsar timing array is bringing us closer to that possibility. By carefully monitoring the arrival times of pulses from dozens of millisecond pulsars scattered across the sky, including some Black Widow systems, scientists hope to detect the subtle influence of passing gravitational waves. These efforts, such as the North American Nanohertz Observatory for Gravitational Waves, NANOGRAV, and its international partners, may eventually allow us to not only listen to the tick of these cosmic clocks, but to hear what stirs the space between them. Consider what this means: that a star, dead for billions of years, can still echo its influence across spacetime in ways we are only beginning to understand. That by tracking its light, its changes, and its silences, we might detect the passing breath of a supermassive black hole merger halfway across the universe. Black Widow pulsars are not just isolated phenomena, they are nodes in a galactic nervous system. Sensitive, persistent, ancient. And with the right instruments, we can eavesdrop on the galaxy's internal conversation. There's also an increasingly speculative idea, still at the fringes of astrophysics but growing in popularity, that advanced alien civilizations, if they exist, might use pulsars as navigational beacons or even information transmitters. This theory rests on the unparalleled precision of millisecond pulsars. Unlike quasars or variable stars, pulsars emit pulses so regular they rival atomic clocks in stability. The idea is that an intelligent species capable of interstellar travel might synchronize its spacecraft or networks using these natural lighthouses. Some scientists have gone further, wondering if the arrangement of pulsars in the galaxy could have been subtly engineered or modulated to carry encoded information. While no evidence supports this idea yet, the notion is compelling because it relies not on constructing new technology, but on harnessing existing cosmic infrastructure. And if you were looking to broadcast a signal across thousands of light-years using something that would endure long after your civilization is gone, a Black Widow pulsar, with its billion-year lifespan and high-energy output, might be just the tool. Even if no such civilizations exist, the metaphor remains powerful. Black Widow Pulsars are beacons. They are ancient, reliable, and uncaring, but we can use them to find our way, to understand the structures that bind the galaxy together, and to measure forces so subtle they defy comprehension. They show us that even the most destructive systems can become instruments of discovery. That decay can become precision. That death can become knowledge. And so, the study of these strange stars continues, not as a curiosity, but as a frontier. Every new discovery about a Black Widow pulsar adds a brushstroke to a cosmic painting we have barely begun to sketch. They inform our models of stellar evolution, they influence our hunt for gravitational waves, and they sharpen our ability to explore time, matter, and energy in their most extreme forms. They are clocks. They are killers. They are teachers. They are secrets wrapped in magnetism and spin. And they will outlive us. Yet even with all we know, Black Widow pulsars remain among the most enigmatic and disturbing celestial objects we've encountered. Their very existence forces us to question the traditional boundaries between life and death, evolution and destruction, silence and communication. When we gaze upon these objects, not with our eyes, but through radio telescopes and the language of light, we're peering into a system locked in cosmic cannibalism. They are, quite literally, undead stars, stripped of their original form, reanimated by the matter and motion of their own destruction. The more we observe these systems, the more they refuse to fit neatly into our current models of stellar evolution. They are not easily categorized. Some Black Widow pulsars show erratic spin-down behavior. Others exhibit unpredictable timing noise. A few seem to straddle the line between Black Widow and Redback classifications, systems where the companion is larger and not yet fully ablated, creating complex behavior due to stronger tidal interactions. Some Redback systems have even been observed switching between accretion-powered and rotation-powered phases, toggling between an X-ray bright state and a radio pulsar state within months or years. These so-called transitional millisecond pulsars blur the lines between categories even further and imply that what we thought were end states may in fact be dynamic, mutable phases in a much longer evolutionary story. One of the most pivotal recent discoveries in this context is the object PSR J1023+0038. Sometimes it behaves like a radio pulsar, sometimes like an X-ray binary. These dual personalities reveal that the line between a fully ablating pulsar and a still accreting one is razor thin. Such systems suggest that pulsar behavior can be far more fluid than once thought, and may undergo cycles over timescales much shorter than stellar lifetimes. They act as though they are trying to decide what kind of object they want to be, consuming, evaporating, accreting, and sometimes going quiet altogether. This raises profound questions about the fate of their companions. In classical Black Widow scenarios, the companion is expected to be whittled down over billions of years until it becomes an unrecognizable, substellar husk, perhaps no more than a few Jupiter masses. But this assumes that mass loss is steady and complete, and that the companion has no means of escape. What if the system destabilizes before total evaporation? What if the companion is flung outward by asymmetric mass loss, or kicked away by gravitational interactions? In such cases, the final product may not be a lone pulsar, but a rogue planet or brown dwarf wandering the galaxy, marked by signs of its violent past. It's a reminder that these systems don't just end, they break apart, leaving relics scattered across interstellar space like pieces of a shattered chronometer. Meanwhile, the pulsars themselves are not immune to fate. While they may continue spinning for billions of years, even millisecond pulsars will eventually slow down. As their rotational energy depletes, they lose the ability to generate strong magnetic fields and high-energy emissions. They fade into obscurity as so-called dead neutron stars, objects so cold and quiet that they're virtually invisible. But before that happens, they may leave behind a trail of evidence: tiny gravitational tugs on nearby objects, low-level emissions, or sudden collapses into black holes if their mass becomes unstable. Even their death is not simple. And yet, their endurance is awe-inspiring. Consider this: a Black Widow pulsar spins hundreds of times per second. If it were the size of Earth, its surface velocity would exceed the speed of light, but instead, Compressed into a sphere just 20 kilometers wide, it rotates with surreal efficiency, losing almost no energy per revolution. The forces holding it together are beyond comprehension: gravity so intense that it crushes atoms, magnetic fields that could erase credit cards from halfway to the moon, and densities so high that a teaspoon of neutron star material would weigh more than all the buildings in New York City. These are not stars in any traditional sense. They are nuclear cores exposed to the vacuum of space, blazing not with light, but with the memory of their collapse. Despite their age, Black Widow pulsars are often found in regions with surprisingly young stellar populations. Some inhabit globular clusters, dense spherical collections of stars orbiting galaxies like ancient halos. These clusters are filled with old stars, but collisions and interactions between them can give rise to new binary systems, setting the stage for pulsar formation even billions of years after the original stars formed. In this way, Black Widow systems can arise from stellar dynamics rather than just chronological evolution. They are not bound to the life cycle of a single star but are the product of a crowded, chaotic environment where gravitational interactions weave and unweave stellar partnerships over eons. In one famous example, the pulsar PSRB 1957+20, commonly known as the original Black Widow, resides in the galactic plane, but its orbital and rotational properties suggest a violent origin. It spins at 622 revolutions per second and has a companion with a mass of only 0.02 solar masses, far below the threshold for sustained fusion. The system emits powerful radio pulses and is surrounded by a Bose shock, a curved wave of gas and plasma sculpted by the pulsar's motion through the interstellar medium. This is a system on the run, dragging its broken partner behind it, leaving a glowing wake in its path like a cosmic predator streaking through space. But for all their ferocity, these systems are also some of the most precise natural instruments in the universe. Millisecond pulsars are so regular in their emissions that they have been proposed as alternatives to atomic clocks for long-term timekeeping. Some scientists even suggest that if humanity ever builds a galactic navigation network for space travel, it will rely not on GPS satellites, but on pulsars, each emitting unique time-stamped signals that could be used for triangulation across light years. Already, spacecraft like NASA's NICER and China's XBNAV-1 are experimenting with pulsar-based navigation. Imagine a future starship aligning itself with a dead star's heartbeat in order to navigate through the void. It's not just science fiction, it's a plausible extension of existing technology. Even here, the symbolism is rich. The same system that destroys its partner, the same object that emits death beams across the galaxy, could one day serve as the lighthouse guiding us through the darkness of interstellar space. It is as if the universe itself refuses to be one thing. It will not be simply cruel or simply kind. It gives birth in destruction. It offers direction in decay. And this may be the most important lesson of Black Widow pulsars. They remind us that complexity and contradiction are not flaws in the cosmos, they are its very essence. These stars are not good or evil. They are processes. Engines. Machines built by physics and chance, grinding through cosmic time with a ruthless elegance that defies simplification. They are terrifying because they are real, and beautiful because they are true. When the last pulse fades and the final atom is torn from the last companion, the pulsar will continue its silent spin for perhaps trillions of years, until quantum effects and proton decay reduce even the neutron star to ash. But long before that, it will have served a purpose beyond survival. It will have taught us what it means to endure, what it means to change, what it means to look into the abyss, and still find rhythm. There is a sobering finality to the story of a Black Widow pulsar, an endgame etched in inevitability. But within that inevitability lies something unexpectedly profound, a cosmic echo of resilience. Though we call them widows for their vampiric tendency to destroy, perhaps a more fitting label would be keepers of time, of secrets, of processes so extreme that they operate on the edge of physics itself. Each of these systems, no matter how obscure or rare, carries an imprint of the universe's darkest and most powerful rules, played out on a scale both intimate and galactic. And while Black Widow pulsars are extreme, they are not isolated curiosities. They form part of a broader family of objects in the zoo of stellar remnants. Objects that reveal not only the outcomes of stellar death, but also pathways for the transformation of energy, mass, and information across the fabric of spacetime. Their close cousins, the so-called Redback Pulsars, for instance, tend to have more massive companions. These companions are not yet fully stripped away and often show significant magnetic activity of their own, leading to flares, winds, and dramatic variability in their light curves. Redbacks are often considered the evolutionary precursors to Black Widows. Over time, with enough mass loss and sustained bombardment from the pulsar wind, a redback can become a Black Widow. This dynamic transition from one phase to another is not just theoretical. It has been observed in real time, across several years, through multi-wavelength data. In a sense, we are watching stars change their identities. This transition zone is critical to understanding the full spectrum of millisecond pulsars. It speaks to a kind of life cycle, a prolonged middle age of violence, where the neutron star, newly awakened and spinning at breakneck speed, begins to consume what remains of its binary partner. This cannibalism isn't just a gruesome curiosity. It's a window into binary evolution itself, a case study in how close stellar interactions shape the final states of massive stars. Indeed, many of the most exotic objects in the cosmos, Type I supernovae, gamma-ray bursts, even some forms of fast radio bursts, FRBs, may ultimately trace their origins to systems like these, where mass transfer, angular momentum, and extreme magnetic fields coalesce into explosions that mark both an end and a beginning. Moreover, the presence of Black Widow systems in unexpected locations, like the galactic halo or the outer rims of globular clusters, has reignited questions about how such systems move. Many show high proper motion, suggesting that the supernova which created the neutron star also imparted a tremendous kick, hurling the system across the galaxy at hundreds of kilometers per second. This means a single Black Widow pulsar can travel tens of thousands of light-years in its lifetime, dragging its disintegrating partner with it, carving a path through interstellar space that carries with it radioactive traces, shock fronts, and magnetic disruptions. Some leave behind glowing trails visible in X-rays or gamma rays, ghostly signatures of their passage through the galactic medium. And these motions are more than just trajectories. They are stories in motion. Every displacement, every measured velocity vector, contains clues about the supernova that birthed the neutron star. If the explosion was asymmetric, as many are, it could launch the system on a hyperbolic orbit out of the Milky Way entirely. Some may already be on such paths, silently escaping the galaxy with companions still bound to their fate, still losing atoms to the wind, still ticking. The stars may die, but the motion carries on. Let's also not forget the astonishing human ingenuity that allows us to know these things. The detection and study of Black Widow pulsars is no trivial task. It requires the coordination of some of the most sensitive instruments ever built, radio observatories like the Green Bank Telescope and the Arecibo Observatory, before its tragic collapse, X-ray satellites like Chandra and XMM Newton, gamma-ray monitors aboard Fermi, and gravitational wave detectors like LIGO and Virgo. Pulsar astronomers must synchronize clocks across continents, apply corrections for Earth's rotation and orbital motion, and filter out terrestrial interference to isolate signals often buried in noise. The timing of pulsars, down to nanoseconds over decades, demands the kind of precision that tests the limits of our technology and our understanding of spacetime. In fact, some of the most exciting potential for Black Widow pulsars lies in their utility as tools rather than just objects of study. These systems can serve as testbeds for fundamental physics, general relativity, equations of state for ultra-dense matter, magnetic reconnection, and even alternative theories of gravity. Their behavior offers clues about how neutron stars deform under tidal stress, how they generate their emissions, and how quantum chromodynamics operates under astronomical pressures. In particular, efforts to constrain the neutron star equation of state, an unsolved problem in nuclear physics, rely heavily on observations of millisecond pulsars and their companions. By measuring the orbital decay of these systems and the Shapiro delay, a relativistic time lag caused by light passing through a gravitational field, scientists can estimate masses with astonishing precision, narrowing the range of possible models for matter under extreme conditions. Some Black Widow pulsars have already yielded shocking results. PSR J0952-0607, for example, is the fastest spinning known pulsar in the galaxy, rotating 707 times per second, faster than a kitchen blender, faster than many mechanical turbines on Earth. It's so fast that its equator is nearly at the limit of centrifugal disruption, meaning it is spinning as quickly as a neutron star can without tearing itself apart. Observing such systems challenges our assumptions about how neutron stars can remain stable, how they manage to radiate energy, and whether even faster pulsars, spinning at over 1,000 revolutions per second, might yet be found. If so, these ultra-fast objects could act as cosmic laboratories for testing the limits of nuclear cohesion and spacetime geometry. As we push forward, newer surveys using instruments like CHIME in Canada and the Square Kilometre Array, SKA, still under development, promise to discover thousands of new pulsars, possibly including many more Black Widows and transitional systems. These discoveries won't just be statistics. They'll be the next generation of case studies, giving us the diversity of systems needed to truly understand this phase of stellar evolution. And perhaps even more thrilling, the deeper we look, the more we increase our chances of finding something weird. A pulsar orbiting a black hole. A system with 2 neutron stars and a planetary companion. A Black Widow whose companion survived long enough to evolve into something utterly unexpected, an exotic degenerate star, perhaps, or an object we don't even have language for yet. In all of this, we are reminded that astronomy is not just the study of light, it is the study of time, of cause and effect, of cosmic narratives written in physics rather than words. The Black Widow pulsar is one such narrative, a brutal but mesmerizing arc that defies simple interpretation. It is a paradox made real, a dead star that spins with new life, a killer that guides us, a destroyer that enlightens. Long after the last human telescope goes dark, long after the Earth itself is dust, some of these Black Widow pulsars will still be spinning. Their companions may be gone, their signals faint, their energy waning, but the legacy of their motion, their precision, their mystery, will echo across time. If anything in the universe can be said to persist, to endure in the face of entropy and collapse, it is the neutron star. And among them, the Black Widow remains the most haunting, because it survives not by chance, but by consuming everything around it. It is survival by devouring, precision born of annihilation, a perfect paradox of violence and order. That is the legacy of the Black Widow pulsar. And that legacy continues to stretch far beyond the realm of academic journals or astrophysical models. It now threads its way into the very frontier of our technological aspirations, the philosophical boundaries of life and death, and even the search for intelligence elsewhere in the cosmos. Indeed, in the bizarre, almost mythological nature of Black Widow pulsars, one begins to see a curious reflection of ourselves. What is perhaps most unsettling, and therefore most intriguing, is the notion that a Black Widow pulsar may, in some abstract but eerily literal way, represent a form of undead star. Not merely a remnant of death, but a transformation into a new state of existence. Just as a virus is not alive in the traditional sense but can propagate and evolve, so too does the neutron star, having undergone the catastrophic death of a supernova, continue on, not simply persisting, but achieving a level of performance, precision, and violence unmatched by its prior life. In this phase, it is more stable, more exacting, and paradoxically more destructive than ever before. The mechanism that drives its actions, the act of consuming a partner, has its mirror in the consumption of information. For us to understand a Black Widow pulsar, we must absorb terabytes of observational data, parse light curves, build timing models, and simulate mass loss across epochs of time. We devour data just as the pulsar devours mass, and in doing so, each of us, the scientist, the observer, even the passive stargazer, is linked to this cosmic story through inquiry and reflection. This raises a startling possibility. Could some Black Widow systems be detectable not just through their radio waves, but through their gravitational signature alone? If the companion is eroded down to a planetary mass object, too dim to be seen directly, then the only clues to its continued existence may lie in the subtle timing delays in the pulsar's emission, or in minute orbital irregularities over decades of observation. And if the companion is finally reduced to nothing, truly consumed, what happens then? Does the pulsar cease to pulse? Does its beam wander unanchored? Or does it continue unabated, now an eternal timekeeper with no counterpart, no anchor, no reference point but itself? This is no small question. Some astrophysicists propose that such lone millisecond pulsars might still carry with them traces of their past, slight asymmetries in spin, peculiar magnetic axis angles, or surface hotspots that mark where mass once accreted. Like fossils, these traits preserve history in silence. We cannot hear the companion scream, but we may read its death in the star's residual motion. In that sense, the neutron star becomes a cosmic witness, its own body a ledger of events no longer observable by any other means. And yet, for all their destruction, Black Widow pulsars also remind us of the universe's subtle equilibrium. They are not merely annihilators. They are also balances. Systems in tight orbital dance, where radiation pressure and gravitational pull are locked in an intense feedback loop. The pulsar may evaporate its companion, but only so long as their separation and orbital momentum allow it. Too much energy too quickly, and the companion may be ejected. Too little, and mass transfer could reverse, resuming accretion. They teeter on the edge of multiple outcomes. Like a candle burning both ends, there's only so long this instability can last before collapse, or equilibrium, wins out. This makes Black Widow pulsars ideal subjects for the study of what's known as feedback regulation in astrophysics, the concept that extreme phenomena can self-regulate through opposing forces. Think of star formation slowed by radiation pressure, or black hole growth tempered by accretion winds. In a Black Widow system, the neutron star's evaporation of its companion both sustains and threatens the very mechanism that keeps it active. It's the closest thing nature has to a paradoxical engine. It consumes to persist, but risks destroying the very fuel it needs to continue. Now, imagine civilizations advanced enough to harness or observe such systems not just as objects of curiosity, but as components of stellar engineering. While speculative, some theorists have considered whether advanced extraterrestrial intelligence might leave signatures near stable, precise astrophysical clocks like millisecond pulsars. If you were to build a beacon across interstellar distances, broadcasting not in symbols, but in rhythm, what better medium than a star that ticks with atomic regularity? Some SETI researchers have even floated the idea that if alien civilizations wanted to build a distributed network of timekeepers or navigational nodes, millisecond pulsars, especially stable ones like Black Widows, would be ideal foundation points. Not because they're intelligent, but because they appear intelligent in their precision. Even without invoking intelligence, the stability of Black Widow pulsars offers practical benefits for us. NASA's Sextant project, for example, successfully demonstrated autonomous navigation using pulsar signals aboard the International Space Station. This, Galactic GPS, uses the precise arrival times of X-ray pulses to triangulate a spacecraft's position without needing Earth-based communication. Future missions to the outer planets, and potentially to interstellar space, could navigate using the dead stars left behind by long-lost suns. One day, a human colony in orbit around Proxima Centauri may use the heartbeat of a Black Widow pulsar thousands of light-years away to keep its clocks synchronized. The irony here is breathtaking. A star that once exploded, that now destroys its partner and rages across the cosmos, becomes the backbone of our effort to explore the stars. A remnant of death becomes a scaffold for life's expansion. Yet no story of Black Widow pulsars would be complete without addressing the ultimate question: how do they die? The fate of a Black Widow pulsar is tied directly to its environment. If it eventually loses its companion, either through total evaporation or orbital disruption, it will become a solitary millisecond pulsar. Over vast timescales, it will lose angular momentum through magnetic dipole radiation and gravitational wave emission. This spin-down process is slow, but relentless. Eventually, the pulsar crosses the so-called death line, a threshold where its rotational energy is no longer sufficient to generate radio pulses. At this point, it becomes a radio-quiet neutron star. Cold, black, silent. But it doesn't stop there. Over trillions of years, far beyond the age of the current universe, the neutron star itself may decay. Quantum tunneling effects could cause the protons in its dense core to decay. The whole star may slowly dissolve into leptons and photons, evaporating not in a flash, but in a whisper. Some theories even suggest it might collapse further into a black hole under specific mass and symmetry conditions, though this remains speculative. Alternatively, in the far future, rogue planets and stellar remnants may fall into long-dead neutron stars, reigniting processes of accretion and magnetic field realignment. Even in death, they may be called back into motion, becoming part of new systems, new feedback loops, new forms of complexity. In the broadest sense, Black Widow pulsars are not endpoints. They are bridges, connectors between different stellar phases, between destruction and utility, between astrophysics and the human imagination. Their story is long, but not linear. Violent, but not cruel. Bizarre, but not irrational. They are the dark poetry of the universe, spinning, blazing, consuming, whispering to us in pulses older than cities, sharper than glass, and stranger than any myth humanity has ever told. We look up at the sky and imagine constellations. But the real stories, those written in radiation, in orbit, in annihilation, play out unseen. Black Widow pulsars are among the greatest of these stories. And we are only just beginning to understand what they're trying to say. In the expanding tapestry of cosmic discovery, Black Widow pulsars remain one of the most paradoxical and electrifying threads. They are simultaneously beacons of supreme precision and agents of absolute destruction, embodying a balance that the universe itself seems to celebrate. Precision forged in chaos, stability born from catastrophe. They sit at the intersection of several astrophysical extremes: magnetism, gravity, velocity, and radiation, and in doing so, challenge the edges of our theories, instruments, and even imagination. What perhaps captures the imagination most deeply is that these systems are not theoretical curiosities. They are real, observable, and increasingly common in our pulsar catalogs. Each newly discovered Black Widow pulsar adds more depth to the enigma. One such system, PSR J1311-3430, stunned astronomers by being the first Black Widow pulsar detected solely through gamma rays. It orbited its companion in just 93 minutes, the shortest known orbital period for any pulsar binary. Its companion, estimated to be less than 8 times the mass of Jupiter, is bombarded so thoroughly by the pulsar wind that it emits a comet-like tail of material streaming behind it. The system is barely holding together. And yet, this extreme instability is precisely what allows us to study it. The pulsar's gamma-ray emissions are pulsed with such regularity that even faint anomalies, millisecond-level changes in timing, can provide volumes of data. These anomalies are not noise. They are messages. They reveal orbital decay, tidal deformation, eclipse characteristics, and magnetic interactions that give us unparalleled insight into binary dynamics and neutron star physics. The light we observe from Black Widow systems isn't only radio or gamma. Some systems emit across the electromagnetic spectrum, from radio to X-ray to optical. In the optical band, we can directly observe the irradiated companion stars. These companions, bombarded by energetic particles from the pulsar, heat up on the side facing the neutron star and glow brightly, while the far side remains much cooler. This results in highly asymmetric light curves when viewed from Earth. Studying these curves allows astronomers to estimate the size, shape, temperature gradient, and orbital inclination of the system. It even allows us to map the day and night sides of a dying star, creating a literal heat map of obliteration. From this data, we learn something else, too. These stars are often no longer spherical. The gravitational forces and intense radiation cause them to become teardrop-shaped, with mass being pulled towards the pulsar in a steady stream. Eventually, this stream becomes a full accretion disk, if it lasts long enough, essentially transforming a rotational energy source into a mass-based feeding mechanism, only for the pulsar to fire back with high-energy jets that heat the disk and shred it. The result? A feedback loop that walks the edge of stellar cannibalism and magnetic rebellion. These processes are not just violent, they are efficient. No natural system rivals the energy conversion efficiency of a pulsar. When compared to human technologies, a Black Widow pulsar makes the most efficient fusion reactor or power grid seem laughable. Even our largest particle accelerators barely replicate a fraction of the energies present in these systems. A neutron star's magnetic field can be 1 trillion times stronger than Earth's. Its rotation can convert a fraction of its mass to energy at rates that rival the output of entire galaxies, per gram. A single cubic centimeter of neutron star matter outweighs Mount Everest. And within that cube, particles are so tightly packed that they may exist as exotic states of matter, quark-gluon plasmas, strange matter, or superfluid cores, states that exist nowhere else in the known universe and cannot be produced in any laboratory. So what does this mean for physics? Quite simply, Black Widow pulsars are among our best natural laboratories for probing fundamental questions. What happens to matter under infinite pressure? Can magnetic fields exceed the quantum critical limit? How do gravitational and quantum forces coexist at ultradense scales? Can general relativity and quantum field theory be reconciled through the observable phenomena of such stars? These questions touch on the very foundation of modern physics. We cannot test these extremes on Earth. But the universe does the work for us. And among its most cooperative test sites are the Black Widow systems, so bright, so violent, and so mathematically rhythmic that they become laboratories in the sky. Even in their more speculative domains, Black Widow pulsars stretch our thinking. Could their extreme conditions create exotic particles, like axions or sterile neutrinos, that are proposed candidates for dark matter? Could they trigger phase transitions in the neutron star core that mirror early universe events? Could their precision timing be affected by cosmic strings or gravitational wave backgrounds, giving us clues about topological defects or higher dimensional phenomena? These are not idle musings. They are active areas of research, increasingly grounded in the observable anomalies in timing residuals or spectrum deviations. The closer we look, the stranger things become. But perhaps the most haunting aspect of Black Widow pulsars is their quiet suggestion that the universe is not kind. It is not cruel either. It simply is, a mechanism of pressure and time, mass and momentum, rotation and field. In this uncaring machinery, even the most extraordinary fates, like being slowly evaporated by your own partner, can become common, repeated across the galaxy, written in waves of energy that carry for tens of thousands of light years. And yet we interpret them. We assign metaphors. We call them widows, monsters, clocks, killers. We romanticize their violence, their paradox, because in doing so, we give shape to the most fundamental insight that astronomy offers. We are not separate from the universe. We are made of it. And when we look into these stars, we are not just gazing into astrophysics. We are watching the machinery that made our atoms, dictated the shape of our world, and allowed the conditions for life to emerge. The silence of space is deceptive. It is filled with stories like these, stars that died and came back as demons of light, consuming their companions in a centuries-long feast of mass and radiation. Black Widow pulsars are terrifying. They are beautiful. And they are true. Perhaps the most remarkable thing about Black Widow pulsars is not just what they do, but what they allow us to become. Students of silence. Keepers of cosmic rhythm. Interpreters of annihilation. And maybe, just maybe, by understanding them, we inch closer to understanding ourselves. But what more could we possibly hope to learn from these celestial assassins, these timekeepers that do not simply outlast but outshine most stars in their efficiency, mystery, and complexity? As it turns out, we're just scratching the surface. In fact, Black Widow pulsars, and their close relatives known as Redbacks, may hold the keys to understanding not just isolated stellar processes, but entire population-level dynamics of the galaxy and beyond. You see, one of the most startling implications of Black Widow systems is the suggestion that millisecond pulsars, particularly those in binaries, might be far more common than previously thought. As our instruments improve, particularly with next-generation radio observatories like the Square Kilometre Array, SKA, the Canadian Hydrogen Intensity Mapping Experiment, CHIME, and new X-ray missions like eerie, we're beginning to uncover a vast hidden population of faint or heavily obscured systems. Many of these are in tight binaries, undergoing active mass transfer or irradiation phases, but appearing dim or intermittent from Earth due to their geometry or absorption by surrounding material. The implication here is massive. It means that the neutron star graveyard, the hypothetical population of all neutron stars ever created, might not be a quiet and settled afterlife at all. It may instead be a seething, active ecosystem of rapidly spinning, magnetized objects and dynamic interactions, consuming companions, reigniting magnetic fields, producing transient high-energy outbursts, and evolving through complex pathways we don't yet fully grasp. And among them, the Black Widows are the loudest. They force us to redefine what it means for a star to die. Because death in astrophysics isn't the end, it's a transition. And in the case of pulsars, it's often a rebirth into something stranger and more extreme. These are the undead stars of the universe. They do not decay into silence. They whisper in perfect pulses. They tear apart other stars not in violence for its own sake, but as a mechanism for survival. They don't simply fade. They evolve. What's even more remarkable is that some of these systems show reversibility. A pulsar can enter a state of accretion and spin up, then return to a radio-loud phase. In rare but well-documented cases, such as PSR J1023+0038, astronomers have observed a pulsar switching back and forth between being a radio pulsar and a low-mass X-ray binary, seemingly in real time. It flips states as though choosing between identities. One moment it devours, the next it pulses. This transitional behavior suggests that the very nature of a pulsar is not static but dynamic, fluid, oscillating, perhaps even cyclical. These so-called transitional millisecond pulsars have become a cornerstone in our understanding of pulsar recycling, the process by which old, slow neutron stars are spun up by accreting matter from a companion. Black Widow pulsars may represent the terminal stages of this cycle, where accretion stops and evaporation begins. But transitional pulsars show us that the lines are not clear-cut. They're messy. They're reversible. They're living systems in the astrophysical sense, where phase changes occur under environmental pressures much like biological evolution responds to ecological pressures. And here, the metaphor becomes more poignant. What if we looked at Black Widow pulsars not just as exotic dead stars, but as participants in a broader ecology of the galaxy? They convert mass into energy, feed on neighbors, influence surrounding gas through jets and winds, and emit radiation that shapes nearby space. Their radiation can strip atmospheres off neighboring exoplanets, trigger magnetic reconnection in nearby gas clouds, and, most critically, serve as gravitational wave sources detectable by future space-based detectors like the Laser Interferometer Space Antenna, LISA. Indeed, in tight orbits, these binary systems emit low-frequency gravitational waves. Though these signals are far below the frequency band of LIGO or Virgo, they may become detectable with pulsar timing arrays, networks of millisecond pulsars monitored across the sky to detect slight irregularities in arrival times caused by passing gravitational waves. If Black Widow systems are sufficiently numerous and extreme, they could become important contributors to the stochastic gravitational wave background, the cosmic hum, produced by countless binary mergers, massive black hole in spirals, and exotic compact object interactions. This brings us full circle. Black Widow pulsars are not isolated. They're nodes in a galactic web of interaction. They signal to us in electromagnetic waves, gravitational distortions, and perhaps, if theories of exotic matter hold true, even particles we have yet to detect. They are both symptom and driver of galactic evolution. And here's where the thought becomes dizzying. These stars, hundreds or thousands of light years away, with masses no larger than a city but gravitational fields strong enough to bend light and time, are shaping not just their immediate environments, but our understanding of time itself. Every pulsar, ticking with sub-millisecond accuracy, becomes a reference point for atomic clocks, navigation systems, deep space probes. In the future, when humanity begins building permanent settlements on the Moon, Mars, or on orbiting habitats, our clocks might be synchronized not by Earth's rotation, but by the remnants of stars that outlived their own systems. In that future, when we speak of time, we may speak in pulses. Black Widow Pulsars may eventually become more than astronomical curiosities. They may become infrastructural. Like lighthouses in space, their beams could guide interstellar traffic, regulate time in autonomous outposts, or be embedded into the architecture of long-range AI systems that navigate and mine the asteroids, terraform planets, or build Dyson-like structures around faint stars. After all, once you understand a thing that precise and that durable, the only logical next step is to use it. There's an irony here so vast it defies simple description. A dead star, having destroyed everything around it, becomes the framework for exploration, synchronization, and progress. In its violence, it brings order. In its isolation, it connects the cosmos. In its darkness, it lights the way. And so the story of the Black Widow Pulsar is not a story of endings. It is the story of transformation, of what happens when the universe, through cataclysm and collapse, engineers some of the most precise, brutal, and beautiful machines ever known. They are clocks, they are killers, they are laboratories, and they are guides. They are, in the truest sense, the strange heartbeats of a universe that never truly sleeps. Even as our understanding of Black Widow pulsars grows deeper with each discovery, so too does the mystery that surrounds them. For with every system we uncover, we are reminded that the universe does not conform neatly to the boundaries we define. Black Widow pulsars, while broadly following the outlines of our theories, continuously present exceptions, outliers that defy classification, systems whose properties seem to hint at hidden variables or undiscovered physics. Take, for instance, the unresolved questions around the mass limits of neutron stars. Many Black Widow systems appear to host neutron stars that push, and sometimes even exceed, the commonly accepted theoretical maximum mass of around 2.16 solar masses. In fact, one of the most infamous examples is PSR J0952-0607, a pulsar spinning nearly 707 times per second, the second fastest spinning pulsar ever discovered. Based on recent measurements and modeling, this neutron star might have a mass greater than 2.3 solar masses, making it one of the most massive neutron stars known to science. Such observations provoke unease in theoretical circles, because they imply that our models of nuclear matter, the physics of matter at densities beyond those in atomic nuclei, might be incomplete or flawed. Neutron stars are not simply neutrons packed together. As pressure increases inside their cores, matter is predicted to undergo transitions, first into exotic nuclear pastes, then possibly into hyperon-dominated matter, quark matter, or even strange matter, composed of equal parts up, down, and strange quarks. But all of these exotic states soften the equation of state, meaning the star should collapse under its own weight at lower masses. If we're seeing stable neutron stars above 2.3 solar masses, then either such states do not form, or we're missing some fundamental repulsive force or structural support, like color superconductivity or a previously unknown pressure interaction. In this way, Black Widow pulsars serve as stress tests for the fundamental laws of matter. They're not only destroying their companions, they're also shattering our assumptions. This is especially potent because we often think of astronomical phenomena as being remote in both space and consequence. But the reality is that the physics of Black Widow pulsars touches everything. It defines the limits of nuclear stability, which underpins all of chemistry. It shapes our understanding of compact object formation, which directly informs supernova modeling and star formation rates in galaxies. And if these systems ever show unexpected radiation behaviors, say, bursts of high-energy particles that don't match any known process, they could provide the first direct evidence of physics beyond the standard model. Moreover, these systems may represent the closing act in a chain of stellar evolution that begins billions of years earlier. Think of it, a star forms from interstellar dust, lives a life of fusion and radiance, collapses into a neutron star, finds a companion, steals mass, spins up, ignites again in a new phase of existence, and then begins to slowly dismantle the very star that extended its life. The life cycle of a Black Widow pulsar is not linear. It's recursive, complex, and profoundly interdependent. It speaks to the universe's ability to create not just structures, but narratives, stories of death turned to rebirth, of partners turned to predators. And just when we think we've understood the theme, we discover a new twist. Enter the Redback Pulsars, systems that are closely related to Black Widows but involve heavier companion stars, often ranging between 0.1 and 0.4 solar masses. These companions are not as far gone. They are often partially stripped, showing signs of being irradiated and deformed, but not yet annihilated. In some cases, they are caught in a delicate balance between mass transfer and evaporation, teetering between survival and dissolution. What makes Redbacks even more fascinating is their instability. Unlike their Black Widow cousins, which tend to emit relatively stable, consistent pulses, many Redback systems are highly variable. They exhibit dramatic swings between being radio-loud millisecond pulsars and low-mass X-ray binaries, sometimes transitioning multiple times over just a few years. These systems are not simply consuming their companions, they are undecided about how. One moment they are accreting, the next they are pulsing, the next they are quiet. These flickering behaviors make them more than just evolutionary precursors. They're living fossils in a state of flux. They also offer fertile ground for gravitational wave research. The rapid orbital decay seen in some Redback and Black Widow systems, caused by intense angular momentum loss through radiation and mass outflows, provides an indirect signal of energy loss consistent with general relativity. Over time, this decay should lead to tighter orbits and, eventually, merger or total evaporation. If these endpoints can be studied in real time, we might be able to constrain alternative theories of gravity, dark sector interactions, or even test the nature of spacetime itself. In fact, there is growing interest in how these systems might fit into the broader framework of galactic evolution. Pulsar binary populations are expected to play a non-trivial role in shaping the ionization history of the galaxy. The high-energy radiation and particle winds from evaporating companions can seed the interstellar medium with plasma, alter local magnetic fields, and influence the formation of nearby star-forming regions. In extreme models, pulsar winds are even invoked as potential explanations for some mysterious fast radio bursts, FRBs, or as accelerators of cosmic rays up to ultra-high energies. And what of the idea that such systems could host planetary debris or even rogue planets? There have been tantalizing hints, particularly in older pulsar systems, that planetary mass bodies can orbit some neutron stars, remnants of destroyed stellar companions or captured interstellar objects. Could some of the dust and matter stripped from evaporating stars and Black Widow systems eventually coalesce into new planets? Could we see, at the end of stellar death, the faint glimmers of rebirth? That question leads us deeper into speculation but not into fantasy. Already, pulsar planets are real. The very first confirmed exoplanets were found around the pulsar PSR B1257+12. And while the environment around a pulsar is harsh, bathed in radiation and magnetic storms, life finds a way, as they say. Or perhaps more humbly, the building blocks of life find a way to endure, to hide, to wait. Because while Black Widow pulsars appear to be about destruction, at their heart is a pattern, a rhythm, a memory of the star that came before, the star that spun too fast, burned too hot, and died too soon. And within that memory, encoded in its perfect pulses, lies information. Information about space, time, mass, matter, and motion. Information that may one day guide our spacecraft, teach our physicists, or even form the time-beating hearts of our distant descendant starships. We are not separate from these systems. We are their outcome. The iron in our blood, the calcium in our bones, the gold in our circuits, they came from the stars that died in cataclysmic supernovae and neutron star mergers. Some of those stars may now be pulsars, whispering back the story of what came before. And when we listen, truly listen, we are not just hearing pulses. We are hearing the echo of the universe building itself. The deeper we plunge into the world of Black Widow pulsars, the more we realize that they aren't just fringe phenomena tucked away in obscure corners of the cosmos. They are foundational anomalies, outliers that defy expectations yet somehow become central to the next generation of astrophysical inquiry. As such, they serve as gravitational touchstones for some of the most profound questions we can ask. How does matter behave at the very brink of collapse? How do stars live on in forms more extreme than their original lifespans allowed? And perhaps most provocatively, could these stellar monsters, consuming and pulsing and evaporating their companions, be precursors to even more exotic objects that have yet to be discovered? That possibility isn't as remote as it may sound. When a neutron star gains mass, either through accretion or merger, it approaches the Tolman, Oppenheimer, Volkoff, TOV limit, the point at which no known force can counteract its own gravity. At this threshold, the neutron star is expected to collapse into a black hole. However, Black Widow pulsars seem to hover at or near this theoretical edge. So if any of these stars were to acquire just a little more mass, could they become something other than a black hole? Could there be a transitional state, a quasi-stable form of ultra-dense matter like a quark star or a strange star? Quark stars are hypothetical objects composed of deconfined up, down, and strange quarks, a form of matter that might exist beyond neutron degeneracy pressure. These stars would be even more compact than neutron stars and could form from the core collapse of a supermassive neutron star. And if Black Widow pulsars are pushing neutron stars to their absolute mass limits, they may be prime candidates for such transformations. We could be witnessing not only stellar cannibalism but the natural laboratories of exotic matter creation. This brings particle physics directly into the astrophysical spotlight. In controlled settings like the Large Hadron Collider, LHC, we can briefly recreate the extreme conditions thought to exist inside neutron stars, but only in tiny volumes and for infinitesimal fractions of a second. Black Widow pulsars, by contrast, provide us with stable, long-duration, ultra-dense environments where such matter may exist continuously. They are, in effect, naturally occurring high-energy physics experiments playing out over cosmic time scales. Moreover, the interaction between the pulsar and its companion, especially the intense particle wind emitted by the pulsar, could be generating an exotic plasma not unlike the early universe's quark-gluon plasma. These winds are highly relativistic, often moving at speeds approaching that of light, and they carry not just particles, but complex electromagnetic structures. Studying them can illuminate processes relevant to cosmic ray generation, shock acceleration, and even the physics of magnetospheres around fast-spinning objects like magnet-ars or accreting white dwarfs. Interestingly, Black Widow systems also represent one of the best testbeds for understanding the so-called death line of pulsars. Traditional models suggest that when pulsars slow down to a certain spin period, or when their magnetic field weakens sufficiently, they should cease to emit radio waves and become invisible. But millisecond pulsars, especially those in binary systems, consistently violate this boundary. Their very existence requires us to redefine the conditions under which pulsars can exist, radiate, and reawaken. The implication is that pulsars are more resilient and more adaptable than previously believed. Even after spinning down, they can be spun up again. Even after falling silent, they can pulse once more. Even after consuming a star, they can remain gravitationally bound to its remnants, holding on to just enough mass to remain active. They are not isolated relics of stellar collapse, they are shapeshifters. And what's more, the evolutionary chain doesn't necessarily end with the total destruction of the companion. In some rare scenarios, the companion star may survive in a heavily stripped-down form, evolving into a white dwarf, or even a planetary mass object orbiting a pulsar. In such cases, we see systems where a rapidly spinning neutron star is orbited by an object smaller than Mercury, yet still gravitationally tethered. Some of these objects may be so low in mass, and so old that they resemble giant rocky planets more than traditional stars, calling into question the boundary between planetary systems and degenerate binaries. If you're starting to feel that these systems blur every line we thought existed, between star and planet, between life and death, between collapse and endurance, you're not alone. That's what makes Black Widow pulsars so intellectually magnetic. They demand that we drop our neat categories and think in terms of continuums. They aren't binaries in the black and white sense. They are spectrums of behavior, of transformation, of interaction. Their light, clockwork regular, ancient, and violent, pierces through dust and distance to reach us. But even that light, despite its precision, conceals layers of complexity. Recent research has shown that the emission patterns from millisecond pulsars like Black Widows aren't as perfectly symmetrical as we once believed. Pulse shapes can shift, timing can drift, and occasional glitches appear, brief, seemingly random changes in spin rate. These glitches may be caused by internal rearrangements within the neutron star's superfluid core, or even by star quakes, sudden shifts in the crust of the neutron star due to stress buildup. Imagine that, a star, so dense that a teaspoon of its material weighs billions of tons, can crack and quake like a planet. And what about their impact on larger scales? Could Black Widow pulsars, and their collective behaviors, influence galactic evolution in measurable ways? It's not outside the realm of possibility. While they don't emit the same vast clouds of ionizing radiation as massive OB stars or active galactic nuclei, their precise timing and high-energy emissions offer something just as powerful: information. Across the Milky Way and beyond, these pulsars act as cosmic lighthouses, offering timing beacons for spacecraft, gravitational wave detectors, and galactic positioning systems. If future humanity were to spread throughout the stars, it wouldn't be the constellations that guide them, but the rhythmic, hyper-accurate pulses of dead stars spinning in the dark. We may someday navigate by the heartbeat of the void. And perhaps, just perhaps, these strange systems are not rare at all. Perhaps they are common, merely hidden from view by distance, alignment, or sensitivity thresholds. As radio telescopes grow more powerful, and as gravitational wave observatories begin to tune into lower and lower frequencies, we may discover thousands, maybe millions, of such systems. Black Widow pulsars could be everywhere, quietly annihilating, pulsing, guiding, transforming. The more we look, the more we see. And the more we see, the more the boundaries of what we thought was possible begin to dissolve. And as those boundaries dissolve, a larger cosmic tapestry begins to emerge, one in which Black Widow pulsars are not just destructive anomalies but key threads woven into the fabric of stellar evolution, galactic dynamics, and perhaps even cosmological structure. What's most compelling isn't merely that these objects exist, it's that they exist with such precision, violence, and longevity, all at once. That they can spin hundreds of times per second, with timing accuracy more stable than any atomic clock made by humanity, while simultaneously engaging in one of the most chaotic and violent interactions in the universe: the slow, calculated annihilation of another star. The very duality of these pulsars, order and chaos, timing and destruction, challenges the narrative we often attach to stellar evolution. In many ways, a Black Widow pulsar is a contradiction made real. It's a dead star that spins like it's alive. It's a corpse with a heartbeat. And within that paradox lies a powerful metaphor for the cosmos: not death, not life, but transformation. Let's consider the broader implications. If Black Widow pulsars can transition between accreting X-ray binaries and isolated millisecond pulsars, then they exist in a state of dynamic identity, not fixed endpoints, but transitional phases that evolve over cosmic timescales. Imagine if we applied that model not only to pulsars but to other types of compact binaries, even to black holes. Are the categories we use, pulsar, white dwarf, black hole, just conveniences for organizing the unknown, rather than hard divisions? Could there be unseen stages or exotic endpoints that we've simply not recognized yet? There's growing interest in using millisecond pulsars, including Black Widow systems, as probes for ultralight dark matter, especially hypothetical particles like axions or scalar fields that could couple weakly with ordinary matter and subtly alter the rotation rates or emission patterns of pulsars. Since these stars are among the most sensitive and stable clocks in the universe, even tiny shifts, perhaps due to dark matter interactions, might be detectable over years or decades. If such a signal were ever found, it would mark the first non-gravitational detection of dark matter, rewriting fundamental physics as we know it. This is more than speculative science. Instruments like the 500-meter aperture spherical telescope, FAST, in China and the Square Kilometer Array, SKA, currently under development are explicitly aimed at expanding the pulsar catalog by thousands of entries. They'll allow us to build vast networks of pulsars, effectively a galactic scale interferometer, that could be used to detect gravitational waves from supermassive black hole mergers or to map the distribution of dark matter with unprecedented resolution. And at the center of these networks may be systems like the Black Widow Pulsars, whose extreme properties make them ideal for precision cosmology. Indeed, the idea that something as violent as a stellar predator could become a foundational tool in understanding the peaceful structure of spacetime feels almost poetic. These systems, which devour their companions with impunity, may simultaneously reveal the whisper of colliding black holes in distant galaxies, or the tug of invisible matter sweeping through the Milky Way. They are both destroyers and seers, celestial oracles wrapped in the skin of supernovae. But their story doesn't end in astronomy or physics. There is something about these systems that also resonates on a human level. In myth and literature, the Black Widow spider symbolizes a creature that consumes its mate, a metaphor for obsession, fatal attraction, or destructive dependence. In the cosmos, the Black Widow Pulsar is a literal embodiment of this metaphor, an object that survives by slowly draining the life from its partner. And yet, far from being purely destructive, this process gives rise to an entirely new class of stars. Without the companion, the neutron star might have remained dormant, cold, undetectable. Through this act of cosmic vampirism, it becomes visible, measurable, reborn in the electromagnetic spectrum. That, too, is transformation, albeit through sacrifice. It makes one wonder what other myths the universe has made real. Is there a celestial version of reincarnation in the recycling of stellar material? A cosmic Ouroboros in the endless loop of matter collapsing and exploding, then reforming again? With every Black Widow system we discover, we are not just mapping space, we are unearthing the stories the universe tells in the language of physics. Even the companion stars, though destined for destruction, may leave behind relics, cores stripped of everything but their heaviest elements, hurtling through space at velocities fast enough to escape the galaxy. These, stellar shrapnel, remnants, ejected by asymmetric mass loss or orbital disruption, could become solitary wanderers, dark, fast, ancient. Some astronomers have proposed that such objects might explain certain hypervelocity stars that seem to be moving too quickly to have come from the galactic core. If confirmed, it would link the tragic demise of a star in a Black Widow system to the broader choreography of stars across interstellar space. And there's one final, haunting implication. If Black Widow pulsars can spin up to extreme speeds by consuming a companion, and if some neutron stars formed in isolation can acquire material from interstellar clouds or rogue bodies, then could there be loner versions of these stars, millisecond pulsars that achieve their velocity not through binary evolution, but by some other, undiscovered means? Could we be missing an entire subclass of millisecond pulsars, orphans that found a way to resurrect themselves without a companion? It's not impossible. We have seen isolated millisecond pulsars. And while most have plausible backstories involving former binary partners, some defy easy explanation. Perhaps they represent another piece of the puzzle, or the first clue to an entirely new one. In that sense, the search for understanding never really ends. The more we learn about Black Widow pulsars, the more questions we find curled like spiral arms around the answers. They remind us that the cosmos is not a closed book of cold facts, but a living manuscript, ever writing itself in the language of light, motion, and time. And perhaps that's what makes them so endlessly captivating. Not just their violence or their rarity, but their narrative, the way they embody the cyclical, paradoxical, evolving nature of the universe itself. They embody contradiction made flesh, if you can call ultra-dense, degenerate matter flesh. They are the remnants of the most violent deaths in the universe, yet they persist with a stability unmatched by anything else in nature. They obliterate their companions, yet they owe their very identity to that destructive partnership. In their endless rotations, they pulse out not only the death throes of stars but also the promise of new understanding. And it's in that paradox where the real mystery lies. The enduring allure of Black Widow Pulsars is not just in their mechanics, though those are endlessly fascinating, it's in what they imply. Every observation of one of these systems is like reading a sentence torn from a much larger book, a cosmic manuscript written in energy, gravity, and decay. And if we can piece enough of these sentences together, maybe we'll begin to grasp the deeper plot, the grand narrative of how matter evolves, interacts, and ultimately transforms itself across cosmic time. Let us not forget that these aren't just rare curiosities, each one is a key. A single Black Widow system allows us to probe general relativity in strong gravitational fields, test the behavior of matter under extreme pressure and density, study plasma physics in high-energy regimes, trace the history of stellar evolution, and refine our understanding of binary orbital mechanics. These are not just stellar objects, they're multidisciplinary laboratories written into the night sky. Even their discovery raises questions about our observational bias. Most of the Black Widow systems we know of have been found in radio surveys, particularly through their pulsed radio emissions. But what about systems where the orientation of the pulsar beam misses Earth entirely? Or where dense plasma clouds from the evaporating companion obscure the signal? Could there be dozens, hundreds, of Black Widow systems hiding in the shadows, unseen not because they don't exist, but because we're not looking at them in the right way? This observational blind spot has led astronomers to consider complementary methods of detection, like gamma-ray surveys. The Fermi Gamma-Ray Space Telescope, for instance, has identified gamma-ray point sources that later turned out to be millisecond pulsars, including some Black Widow candidates. The idea is that even if the pulsar's radio beam doesn't intersect Earth, its gamma-ray emissions might still leak through and betray its presence. This hints at an entirely untapped reservoir of invisible monsters lurking in our galaxy, waiting to be unmasked by the right lens. Then there's the role of gravitational waves. Though most Black Widow systems are not massive enough to be strong emitters of gravitational waves, their extreme dynamics, especially during the final stages of companion evaporation or orbital decay, may produce ripple signatures detectable by future low-frequency observatories like the Laser Interferometer Space Antenna, LISA. Imagine tracing the gravitational echoes of a star being shredded apart over millions of years by its collapsed partner. That's not science fiction. That's the frontier of astrophysics. There's even theoretical speculation about what happens to the very last shreds of the companion. Do they get fully absorbed? Do they form a disk? Do they collapse into some exotic structure themselves? Some models propose that the pulsar wind might be so intense in these final moments that it completely halts accretion and blows the rest of the material away in a violent, final flare, an end to the cosmic cannibalism. Others wonder whether in some extreme cases, mass transfer could cause temporary instabilities in the neutron star's outer layers, leading to abrupt changes in pulse behavior or even momentary collapse phenomena. And of course, all of this has broader implications for the ultimate fate of matter. Stars live and die. But neutron stars, especially millisecond pulsars, seem to exist on a longer arc, one where death leads not to silence but to rebirth through destruction. It's as if the universe refuses to waste the matter it forged in its crucibles. It reuses it, reshapes it, and, in the case of Black Widow systems, places it into orbits of endless sacrifice. There is something deeply haunting about that. Yet also, in a strange way, something hopeful. Because in the great silence of space, Black Widow pulsars speak. They speak in radio waves, in gamma flares, in gravitational ripples, in companion destruction, in regularity that defies chaos. They speak of the end of stars, yes, but also of new forms emerging from that ending. New systems. New phenomena. New science. It's no wonder, then, that astronomers remain captivated by them, not merely as anomalies, but as archetypes. As symbols of how the universe behaves when pushed to its most extreme limits. They are as much philosophical objects as they are physical ones. For what could be more existentially rich than a star that dies, revives itself by devouring its partner, and then pulses out the rhythm of that cannibalistic resurrection to the cosmos? In a way, Black Widow pulsars are like cosmic mirrors. They reflect back our deepest curiosities, about death, transformation, isolation, partnership, time, and the ultimate fate of things. They ask us to reconsider not just how stars die, but how death itself might be reimagined, how it might be merely a bridge to a stranger form of life, one stripped of warmth and complexity, yet governed by perfect order. As we point our telescopes at the heavens and try to read the pulses they emit, we are doing more than just collecting data. We are eavesdropping on the oldest stories in the universe. Stories of fire and collapse, of hunger and annihilation, of timing and fate. And somewhere, far beyond what we can currently see, another such story is unfolding. Another companion is being stripped, atom by atom. Another neutron star is spinning up. Another pulse is beginning its journey across the void, racing toward Earth, where, perhaps years or decades from now, it will be detected, analyzed, and folded into the expanding story of what it means to exist in this ever-dark, ever-burning cosmos. It is in this unfolding that the true power of Black Widow Pulsars becomes clear, not just as astrophysical entities, but as agents of revelation. These are not passive objects, they are active participants in the universe's most intimate processes, dragging hidden truths into the light through their extreme behavior. Every cycle of their spin, every vaporized atom of a companion star, every shift in orbital decay tells us something about how matter, energy, and gravity behave at their limits. It's as though the cosmos has built these bizarre systems to test the boundaries of its own laws, and we, by observing them, become witnesses to those stress tests in action. What makes this even more staggering is that all of this unfolds not in distant, inaccessible galaxies, but within the Milky Way, our own galactic backyard. Many known Black Widow pulsars are located thousands of light-years away, which may seem vast, but in cosmic terms, it's remarkably close. These aren't stories from the early universe, locked behind walls of redshift and ancient starlight. They are modern, active dramas playing out right now, their signals already on their way toward our detectors, or even arriving as we speak. But even within our galaxy, they are rare. Not every neutron star becomes a millisecond pulsar. Not every millisecond pulsar finds a companion to strip. Not every stripping process leads to the Black Widow scenario. It's a multi-tiered selection process, a cosmic filtration through which only the most extreme systems emerge. This rarity makes them valuable but also enigmatic. Statistically, they shouldn't be as visible as they are. The fact that we have found so many, even with our limited detection methods, suggests that either we are catching them at a particularly luminous stage in their lives, or there are more of them hiding in forms we haven't yet learned to recognize. That's where the role of theoretical modeling becomes crucial. Astronomers use sophisticated computer simulations to understand how these systems evolve over millions and billions of years. They simulate how neutron stars and low-mass companions interact, how mass transfer occurs, how angular momentum is redistributed, how radiation pressure from the pulsar affects the companion's atmosphere. These aren't static simulations. They are dynamic, nonlinear, and complex, with chaotic feedback loops and tipping points. One change in mass ratio, or spin period, or orbital distance can fundamentally alter the system's fate. It could become a stable millisecond pulsar, or it could spiral into merger, or it could eject the companion entirely and become isolated. And sometimes, things get even stranger. Some theorists suggest the existence of transitional millisecond pulsars, systems that oscillate between being X-ray binaries and radio pulsars, depending on how much mass they're currently accreting. These systems may act like Black Widow pulsars during one phase, then switch behaviors entirely as conditions change. The idea is that pulsars may not be in fixed states but rather fluid ones, evolving over time based on environmental input. It's like watching a predator change its hunting style as prey becomes scarce. The implication here is profound. Maybe the categories we've constructed, radio pulsar, X-ray binary, millisecond pulsar, Black Widow, are merely snapshots of a deeper, ongoing transformation. That transformation may even extend to the neutron star itself. As the pulsar accretes more mass and spins up, its internal structure could be altered. There are models proposing that the immense pressure inside a rapidly spinning neutron star might eventually lead to a phase transition, into quark matter or some other exotic state. If true, then Black Widow pulsars might not just be endpoints of stellar evolution. They could be gateways to discovering new forms of matter, new physics entirely. Imagine a neutron star so extreme in its properties that it collapses not into a black hole, but into something we haven't yet named. There's also the possibility that Black Widow systems could serve as indirect detectors of physics beyond the standard model. For example, if hypothetical particles like axions or sterile neutrinos exist, they might subtly interact with the pulsar's emissions or the companion's atmosphere. Over long observational periods, these interactions could produce anomalies, slight irregularities in timing, spectral output, or energy loss that point toward entirely new realms of physics. In this sense, every Black Widow system is a natural laboratory, one we didn't build but were lucky enough to find, already running. Meanwhile, the companions themselves, the victims in this astrophysical murder mystery, are not entirely silent. Some have been detected optically, often as faint, flickering stars distorted by their proximity to the pulsar. Their light curves show dramatic variability, caused by tidal forces, heating from the pulsar wind, and even material flowing from their surfaces. These flickers are not just observational quirks. They are the screams of stars being slowly torn apart, their surfaces boiling away into nothingness. To detect one is to catch a glimpse of a death spiral in progress, a stellar execution carried out over eons. There's poetry in the fact that we can see these flickers at all. Light from a dying star, distorted by relativistic effects and warped by gravitational tides, travels thousands of light-years across interstellar space just to reach a telescope on Earth. When we detect it, we are seeing both the violence of the moment and the ancientness of its journey. It's as if time itself is folded into the data, moments of extinction layered with millennia of travel, converging in a single photon striking a CCD sensor on some remote mountain peak. That's what makes astronomy so deeply emotional. We are not just studying distant objects. We are catching echoes of violence, whispers of transformation, relics of survival. And Black Widow pulsars are among the loudest echoes, the brightest whispers, the most enduring relics. They're not just reminders of what stars can become, they are reminders of what the universe is always doing, pushing limits, testing boundaries, and creating new forms from the wreckage of the old. This cosmic cycle of destruction and creation, laid bare in the behavior of Black Widow pulsars, touches on something deeply philosophical, the idea that even in the universe's most violent events, there is order, structure, evolution. In these systems, we are witnessing the afterlife of stars, but not in a silent, graveyard sense. It's a loud, brutal, transformative process where death isn't a final state but a catalyst for new dynamics. The neutron star, long dead in its traditional stellar sense, becomes more active than ever before, devouring, emitting, accelerating, dominating. The corpse doesn't just rise, it rewrites its role in the universe. This is particularly fascinating when we think about millisecond pulsars as cosmic timekeepers. They are so precise that their pulses can rival atomic clocks. Their incredible rotational stability makes them ideal for studying minute perturbations in spacetime itself. In a way, Black Widow pulsars are both destroyers and archivists, demolishing their companions while encoding the precise physics of that destruction in their timing. Each tick of their spin is a data point in a vast cosmic experiment, measuring the very fabric of reality. It's like watching the clockwork of the universe run in reverse, with each gear tooth sharpened by gravitational waves, magnetic fields, and relativistic physics. And there's more. One area where Black Widow pulsars are beginning to draw increasing attention is in the search for dark matter. Dark matter, the invisible substance that makes up the majority of the universe's mass, still eludes direct detection. But if it interacts, ever so slightly, with ordinary matter, or if it forms dense clumps, then Black Widow pulsars might feel its presence. Subtle anomalies in their spin-down rates, orbital decay, or companion mass loss might betray interactions with the dark matter halo or passing stream. In this way, studying these violent binaries might not only help us understand their nature but also illuminate one of the greatest remaining mysteries in cosmology. This opens the door to a new kind of astronomy, one that isn't just about seeing, but about inferring. It's an astronomy of deduction, where hidden forces leave visible fingerprints in systems pushed to their limits. And nowhere are those fingerprints more deeply etched than in Black Widow binaries. They react to gravitational tides, particle wind pressure, electromagnetic torques, and relativistic drift in ways that can be modeled, tested, and refined. In short, they are diagnostic tools, sharp instruments crafted by the universe itself for the dissection of its own secrets. And just when you think it couldn't get more complex, enter the Redbacks. Closely related to Black Widow Pulsars, Redback systems involve pulsars with slightly more massive companions, typically around 0.2 to 0.4 solar masses. While Black Widows are often in the late stages of devouring their companions down to planetary masses, Redbacks are caught earlier in the process. They still have substantial stellar companions, and those companions are often bloated, unstable, and distorted by the neutron star's influence. Redbacks may one day become Black Widows, or they might not, depending on how the system evolves. But either way, their very existence fills in a vital part of the evolutionary timeline. They show us what comes before the total annihilation, before the orbital shrinkage and spin-up are complete. Redbacks exhibit something else intriguing: they can switch states. Some are known to transition between being powered by rotation, like standard pulsars, and being powered by accretion, more like X-ray binaries. These transitional millisecond pulsars, caught oscillating between identities, defy the binary categorization that used to define neutron star evolution. They're both pulsar and accretor, destroyer and feeder, remnant and engine. In watching them shift, astronomers gain a glimpse into the chaotic middle stages of stellar cannibalism, a phase filled with unpredictability, sudden flare-ups, and complex radiation signatures. Now, consider the human side of this. Think of the scientists who dedicate their lives to studying these systems, watching tiny variations in pulse timings, reprocessing radio emissions late into the night, simulating magnetic field interactions across entire star systems. What drives them isn't just curiosity. It's the recognition that in these pulses lies the truth of how extreme matter behaves, how binary systems evolve, how general relativity holds up under pressure, and how the story of stellar life and death is far richer than we ever imagined. We're not merely looking at neutron stars. We're looking at mechanisms of transformation. We're watching nature's most extreme recycling program in action. The universe doesn't discard its dead, it reincorporates them into new and strange forms, each one bursting with insight. The atoms forged in supernovae find new expression in these ultra-dense cores. The gravitational energy stored in a collapsed star finds new life in electromagnetic pulses. The sacrifice of a companion star fuels a new kind of order, violent, yes, but coherent, measurable, and surprisingly elegant. What's also striking is how little of this was predicted in advance. The concept of a neutron star itself was once theoretical. The idea that they could spin so fast was shocking. The fact that they could consume a companion and emit measurable pulses with atomic-level precision was unimaginable. And yet here we are, not only observing these phenomena but using them as tools to ask even deeper questions. Could there be more exotic systems still unknown? Perhaps pulsars that have consumed two companions? Could a neutron star fully evaporate its companion and go rogue, traveling alone through the galaxy, a solitary emitter of perfect radio rhythm? Could collisions between Black Widow pulsars and other dense objects, white dwarfs, rogue planets, or even other neutron stars, generate bursts of high-energy radiation or gravitational waves unlike anything we've yet recorded? These aren't idle questions. They're becoming testable hypotheses as technology improves. As telescopes like the Square Kilometre Array, SKA, come online, the number of discovered millisecond pulsars is expected to explode. The hidden zoo of galactic predators will suddenly be made visible, and with it, the evolutionary tracks of their victims and offspring. We'll no longer just have a few well-studied cases. We'll have a population large enough for real statistics, real patterns, real evolutionary modeling. We'll be able to map the life cycles of Black Widow systems from their earliest stirrings to their final evaporated pulses. And perhaps that's the most exciting part. We are not done discovering what Black Widow pulsars are. We are still in the earliest chapters of their study. For all their mystery, they may only be the beginning, a prelude to even more dramatic stellar phenomena that will emerge from the shadows as our instruments sharpen and our understanding deepens. The story of the cosmos, it turns out, is not written in fire alone, but in magnetic fields, time delays, flickering companions, and relentless, consuming hunger. And few tell that story more dramatically than the Black Widow Pulsars, cosmic assassins, reluctant archivists, and shimmering echoes of stars long gone, still whispering truths into the void. But as we move deeper into the narrative of Black Widow Pulsars, we begin to see that these objects are not just astrophysical oddities. They are windows into the fundamental questions of existence itself. At first glance, they might appear to be mere points of light, hidden among the infinite tapestry of the cosmos. Yet the reality is far more profound. Each one is a theater of cosmic violence and evolution, unfolding over eons with the precision of atomic machinery and the intensity of nuclear fury. They are the embodiment of contradiction, dead stars that give rise to the most vibrant activity, destroyers that illuminate the mechanics of the universe, and chaotic systems that yield some of the most predictable timing signals known to science. In studying them, we are forced to confront the limits of our understanding of matter. For instance, the core of a neutron star, where densities reach beyond what we can recreate in any laboratory, may contain exotic phases of matter that defy classical descriptions. The intense gravity crushes atomic nuclei into a soup of neutrons, and perhaps even deeper into quark-gluon plasma, hyperons, or other unknown states of matter. This is where quantum mechanics meets general relativity, and where even the most robust physical theories start to fray. In Black Widow Pulsars, where the neutron star continues to spin up, accrete, and evolve, we might be watching matter under the most extreme compression known in the universe. What could this reveal? For one, if we can determine the precise mass and radius of a neutron star in such a system, we might constrain the equation of state. For ultradense matter, a critical unknown in modern physics, different internal compositions predict different sizes and masses for a given rotation rate. Observations of pulse arrival times, gravitational lensing of the companion's light, and X-ray emissions all serve as clues in this pursuit. In this sense, the Black Widow is not just devouring a star, it is feeding our understanding of the cosmos' deepest secrets. But the intrigue doesn't stop there. One of the most shocking revelations came in 2021, when astronomers discovered a Black Widow pulsar with a mass approaching or possibly exceeding 2.35 solar masses, far greater than the commonly accepted upper limit for neutron stars. If verified, this would challenge our models of stellar collapse and suggest that either neutron stars can sustain far greater densities than expected or that this object is in some transitional state, perhaps even a precursor to a black hole. Could there be a class of pulsars that teeter on the brink of black hole formation, their rotation and internal pressure barely holding off collapse? These borderline cases may be more common than we think, and Black Widow systems, due to their continual mass accretion, may be the most likely to reach such thresholds. The dynamics of these binaries also offer insight into stellar population formation and galactic evolution. Black Widow systems are often found in globular clusters, where the density of stars increases the likelihood of close encounters and binary formation. In these environments, stellar dynamics lead to interactions where pulsars can capture new companions or exchange partners, creating unusual binary systems that might never form in isolation. Studying how Black Widows behave in these dense environments helps us understand how galaxies themselves evolve, and how stellar remnants shape the fate of their surroundings over billions of years. This raises another provocative point. If these systems are so efficient at devouring and transforming their companions, could they also affect planetary systems? Could a planet caught in the wrong orbit be stripped of its atmosphere, or even torn apart by the pulsar's wind? And could this lead to the creation of exotic, degenerate planetary remnants, worlds made not of rock and gas, but of compressed exotic matter, orbiting a spinning neutron star? There is speculative evidence for planetary bodies around pulsars. Some of the first exoplanets discovered were found orbiting a pulsar, in fact. But could those be the debris left behind after a Black Widow event? Could we be observing the skeletal remains of once lush systems, reduced to dust and cores by relentless pulsar radiation? The implications stretch into the future of cosmic evolution as well. Imagine a time when most stars have burned out, when white dwarfs have cooled into black cinders, and the universe is dominated by compact remnants, black holes, neutron stars, and fading brown dwarfs. In such a universe, Black Widow-like systems could continue operating, slowly erasing the last vestiges of stellar companionship through millisecond pulses. They could become some of the final dynamic systems in the cosmos, still rotating, still emitting, long after all traditional sources of light have gone dark. And even now, in our own time, they act as tools of detection beyond their own stories. Because pulsars are such accurate clocks, scientists use arrays of them across the galaxy, known as pulsar timing arrays, to detect gravitational waves on massive scales. Black Widow pulsars, with their tight orbits and complex timing variations, may seem like messy contributors to this effort, but in fact, their sensitivity to perturbations makes them powerful detectors. A passing gravitational wave could shift the timing of their pulses ever so slightly, and by comparing this with other pulsars across the sky, we may be able to triangulate the presence of cosmic ripples generated by supermassive black hole mergers or other exotic events. In essence, these systems are multipurpose. They're not just fascinating in and of themselves, they are part of the observational infrastructure that could unlock the next major discoveries in physics and astronomy. They force us to think differently about binaries, about neutron stars, about the aftermath of stellar collapse, and about the strange, creative chaos of the universe. They are the messy rooms where nature does its wildest experiments, and they don't conform to our neat categories or theoretical expectations. There's something almost mythological about them. The image of a star being drained, digested, and ultimately erased by its once lifeless companion. And yet these aren't myths. They are real. They are measurable. They are glowing on telescope monitors, shifting on spectral graphs, whispering across the electromagnetic spectrum. They are the truth, stranger than fiction, more dramatic than any fantasy. And the best part? We are only beginning to understand them. The deeper we look, the more questions emerge. How stable are these systems over time? Can a Black Widow system reignite its companion's fusion temporarily? Could gravitational wave emission alone push the binary into instability? Could some of these systems be hidden among the hundreds of yet undiscovered radio sources in our sky, waiting for the right instruments to uncover them? As we continue the search, the pulse of the Black Widow grows louder in our ears, not as a warning, but as a song. A song of endings and beginnings. A song of devouring and revealing. A song that echoes through the dark, carrying the secret music of the stars that refuse to die quietly. Yet even in all this grandeur, we must not forget the eerie quiet that surrounds these systems in deep space. Black Widow pulsars are extraordinarily violent, but their stage is absolute silence. No sound, no atmosphere, just radiation, magnetic fields, and the deafening roar of physical laws playing out in silence. Their wind, a flow of charged particles accelerated to relativistic speeds, is invisible to the eye, and yet its impact is devastating. It strips atoms from a nearby star. It reshapes orbits. It blasts away atmospheres. And all of this occurs in the still vacuum of space, under the watchful gaze of our telescopes. This contradiction, the invisibility of violence, the quiet of cataclysm, adds another layer of fascination. The pulses we detect on Earth are just tiny signals, flickers picked up by massive dishes and carefully timestamped by ultra-precise computers. But those flickers represent something much larger. Each one is a snapshot of destruction, a whisper of mass loss, a hint of gravitational grip tightening. And because those flickers repeat so perfectly, we can use them like sonar pings in a cosmic cave, mapping unseen companions, probing the vacuum, even detecting minuscule shifts in spacetime itself. Scientists often refer to pulsars as lighthouses of the cosmos, but Black Widows feel more like searchlights, scanning, targeting, consuming. Their beams don't just illuminate, they punish. They scour their surroundings, creating a radiation zone so intense that it physically sculpts the matter around them. The companion star becomes asymmetric, misshapen, stretched by gravity and stripped by winds. If we could see such a binary up close, it would look grotesque. One star a glowing sphere, the other a scarred, emaciated ghost of its former self. A relationship reduced to one-sided consumption. In some systems, astronomers have even observed what appear to be eclipses caused not by the star itself, but by clouds of plasma blown off the companion into the orbital path. These thick clouds can obscure the pulsar signal for seconds or minutes at a time, indicating the sheer quantity of matter being ejected. Think about that. A star is being carved apart so violently that it builds a shroud around the system, almost like a funeral veil drifting through space. And as we trace these systems across time, we begin to see another layer of relevance. They offer a mirror, not just for the universe, but for human understanding itself. For centuries, humanity imagined stars as eternal beacons, unchanging, divine, fixed. But now we know they live, burn, die, collapse, spin, devour, and re-emerge in altered forms. The Black Widow Pulsar is the ultimate expression of that knowledge, a reminder that even death is not final. That in the remnants of destruction lies the architecture for something new. Something smaller, faster, darker, but far more revealing. There's also a cosmic irony here. We often picture black holes as the final stage of stellar evolution, an object that consumes everything and emits nothing. But Black Widow pulsars are, in some sense, even more complex. They don't vanish behind an event horizon. They shine. They reveal. They measure. They preserve just enough of their past to tell a story, but they are firmly rooted in the present, pulsing, radiating, changing the universe around them. They show us that not all deaths in space lead to silence. Some lead to acceleration, to timing, to the rebirth of data from the ashes of stellar violence. And the diversity of these systems only deepens the mystery. Some spin at over 700 times per second. Others show irregularities in their pulses due to the interaction with their companion's wind. Some have companions barely larger than Jupiter, stellar cores stripped down to planetary masses. Others are in the process of becoming Redback systems again, perhaps gaining mass or shifting energy states. The boundaries between classifications are porous, constantly in flux. This isn't a static category, it's a spectrum of evolutionary paths, all revolving around the magnetic monster at the center. Moreover, the physics at play is staggering. General relativity dominates the orbital dynamics, especially in tight binaries. Time dilation, gravitational redshift, and orbital decay from gravitational wave emission are not just theoretical, they are measured directly. These effects allow scientists to test Einstein's equations in real-world conditions impossible to replicate on Earth. Each Black Widow system becomes a miniature laboratory of relativistic physics, functioning on a cosmic stage millions of light-years away. And then there's the potential for collapse. What happens when a neutron star crosses the threshold into becoming a black hole? Theoretical models suggest that further accretion in a Black Widow system could push the neutron star over the limit. But the collapse might not be instantaneous. Some suggest it could involve a final period of hyperactivity, a death spiral where the pulsar emits a final burst of gravitational waves, an ultimate flare of radiation, and then, nothing. A quiet that's not a pause, but an ending. What could we learn from such an event? Could a Black Widow's transformation into a black hole be witnessed in real time? To answer that, we'd need incredible luck and perfect instrumentation. But the possibility itself reminds us how dynamic and unfinished the universe is. How the laws we think are settled still have realms to explore. And Black Widow pulsars, violent, precise, mysterious, are right at the heart of that exploration. Their very name, inspired by the spider that devours its mate, is a poetic truth wrapped in astrophysical rigor. We didn't choose it lightly. It carries weight. It hints at danger, at betrayal, at beauty edged in death. And these systems live up to the name. They are one of the most extreme, intimate, and revealing phenomena we've yet uncovered. Their study is not just an investigation of stars, but of the very process of transformation, how matter becomes energy, how orbits decay, how collapse births rotation, and how the dead can dominate the living. And perhaps, in the far future, When the last galaxies fade and the universe approaches heat death, it will be these systems, or their descendants, that pulse on. Ancient, unrecognizable, but still spinning, still emitting, still whispering to any listener that the story of stars never truly ends. And that story, still unfolding in the silence of the cosmos, continues to challenge every assumption we've made about how stars live and die, about the boundary between object and environment, and about the delicate dance between creation and destruction. The more we observe Black Widow pulsars, the more we realize that these systems blur the lines we've drawn. They're binaries, but they act more like single dynamic systems. They're destroyers, but they reveal far more than they erase. They are the universe at its most raw, unfiltered, unsympathetic, but deeply instructive. Take, for example, the precision with which these pulsars rotate. The most rapidly spinning neutron star ever recorded, PSR J1748, 2446 AD, spins at an astonishing 716 times per second. That's faster than the blades of a kitchen blender, all compacted into a sphere just 20 kilometers across. The centrifugal force at the equator of such a star is extreme, held in check only by gravity and the ultra-dense equation of state inside. If it spun much faster, the star might fling off matter or even disrupt itself. These boundaries, the edges of what physics allows, are where Black Widow pulsars live. And yet despite their speed and violence, they are stable. Pulsars, especially millisecond pulsars, maintain their rotation rates for incredible spans of time. The regularity of their pulses rivals or exceeds the best atomic clocks on Earth. So when these pulsars change, when a single pulse arrives a few microseconds late or early, it means something. It's a signal. A shift in orbit, a tug from a companion, or the gravitational nudge of a passing wave in spacetime. Every deviation is data. Every pulse is a probe into a physical regime we can't reach any other way. This is why astronomers have turned Black Widow systems into living observatories. By monitoring them over months, years, and even decades, researchers can track orbital decay, mass transfer, and evolution with exquisite detail. And what they've found is remarkable. Some systems are decaying faster than expected, suggesting more efficient mass loss than theory predicts. Others show erratic eclipses and flaring, possibly due to magnetic activity on the companion star, like solar flares, but influenced by a nearby neutron star spinning hundreds of times a second. It's like watching space weather in a supercharged environment where the rules of Earth no longer apply. Some Black Widows also exhibit a phenomenon known as ablation-induced Roche lobe overflow. This technical term hides an elegant and terrifying process. The pulsar's radiation and particle wind heats one side of the companion so intensely that it expands, overflows its Roche lobe, the gravitational boundary of its orbit, and spills mass directly onto the pulsar. The system becomes a kind of death spiral, where radiation feeds mass loss, which feeds more radiation, a feedback loop spiraling into extinction. Over time, the companion may lose so much material that it becomes undetectable, leaving behind a solitary millisecond pulsar. These isolated millisecond pulsars are thought to be the final state of many Black Widow systems, a ghost of a relationship, the devourer left alone. But sometimes, the remnants may not be entirely gone. Recent studies suggest that some systems might retain planetary mass companions, leftovers from the original star, or perhaps planets that somehow survived the chaos. These objects are small, dense, and cold, orbiting what used to be a binary system turned into something quieter. Could these tiny companions hold clues to the evolution of the system? Could they even resemble the fate of our own solar system billions of years from now, when the sun dies and its remnants wander alone? The idea seems remote, but it's not entirely science fiction. Pulsars, after all, were the first stellar objects to be discovered with exoplanets. In 1992, astronomers Alexander Woolson and Dale Frail detected planets orbiting PSR B1257+12, a pulsar with at least 3 rocky planets in close orbit. These weren't Black Widow pulsars, but the principle applies: planets can survive extreme cosmic events. And if they can survive a supernova and a pulsar wind, could they evolve into something new, world shaped by millisecond timing and radiation storms? These questions are speculative, but they're grounded in real observations. That's what makes Black Widow Pulsars so compelling. They don't just push science forward, they provoke it. They raise questions we hadn't thought to ask and challenge us to rethink what's possible. And there's still so much more to learn. Do all millisecond pulsars begin as Black Widow systems? Or are there other paths to extreme rotation? Could some neutron stars be born spinning this fast? What distinguishes a Black Widow from a Redback? Is it just mass, or are there deeper magnetic or structural differences? Could we someday detect gravitational waves from these systems, not from mergers, but from the subtle mountains, on their crusts that distort their spin just enough to ripple spacetime? The technology to answer these questions is advancing rapidly. Instruments like the 500-meter aperture spherical telescope, FAST, in China and the upcoming Square Kilometer Array, SKA, promise to detect thousands of new pulsars, including many more Black Widow candidates. Each discovery will add a new point of data, a new perspective on stellar death, and a new challenge to theory. And perhaps most exciting of all, these systems might help us detect gravitational waves in a whole new frequency band, not from colliding black holes, but from slow, massive undulations across the cosmos. In this way, Black Widow pulsars may hold the key to the next great era of multi-messenger astronomy. They emit in radio, X-ray, and gamma-ray wavelengths. They're sensitive to gravitational waves. They can even help map the interstellar medium by showing how their pulses scatter and disperse across space. Each one is a multidimensional signal, a complex broadcast from a system undergoing real-time transformation. They are messengers, not just of stellar death, but of universal structure. And what's more, they are still hidden in plain sight. For every known Black Widow, there may be dozens or hundreds more waiting to be found, too faint, too shrouded in plasma, or too complex in their timing to be identified yet. The universe is full of secrets. And these pulsars, wrapped in their cloaks of radiation and plasma, may be hiding in the static, pulsing silently until we have the tools to hear them. One of the most profound truths about Black Widow pulsars is that they represent not just a physical transformation, but a conceptual evolution in our understanding of the cosmos. When pulsars were first discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish, they were so precise, so regular, that for a brief moment, they were nicknamed LGM. Little Green Men, because such an orderly signal seemed alien. Today, decades later, we understand these signals not as signs of extraterrestrial intelligence, but as relics of stellar violence, spinning at unimaginable speeds, stabilized by the very fabric of spacetime. Yet, in the case of Black Widow pulsars, that sense of alienness has returned, not because we think they're unnatural, but because they are so extreme, so counterintuitive, that they seem almost otherworldly. This extremity is what makes them so valuable. In science, edge cases are often the most illuminating. In the extremes, we find the limits of our theories, and it is there that those theories either evolve or collapse. The Black Widow pulsar is such an edge case, the fastest rotations, the tightest binaries, the most efficient systems of mass destruction ever seen. These pulsars are clocks, yes, but they are also weapons, stripping entire stars down to their cores, and even then, pushing beyond that. One of the strangest implications of these systems is that they can help us understand how matter behaves under pressures and densities that would annihilate anything on Earth. Inside a neutron star, especially one spinning at hundreds of times per second, the matter is packed so densely that atoms collapse, electrons and protons fuse into neutrons, and beyond that, perhaps into exotic particles we've never seen. Quark-gluon plasma? Strange matter? The core of a Black Widow pulsar may be one of the only places in the universe where such states exist naturally. And we can't observe them directly. We infer their presence through pulse timing, X-ray spectra, and theoretical modeling. But we're getting closer. Advanced instruments like NASA's Neutron Star Interior Composition Explorer, NICER, mounted on the International Space Station, are already providing X-ray pulse profiles from rapidly spinning neutron stars. By measuring how light curves as it leaves the surface of a neutron star, bent by its intense gravity, we can begin to map its size and mass, and in doing so, test equations of state, the rules of matter at supernuclear densities. Black Widow Pulsars, because they often involve ongoing accretion or strong particle winds, present even more variables to work with. The way their emissions shift. The way their companions change shape or lose mass. The orbital decay. Each of these is a probe into the interior of an object we can't touch. In this sense, black widows are not only cosmic predators, but also cosmic laboratories, torturous, yes, but revealing. And the more we learn, the more questions arise. Why do some pulsars turn on suddenly, spinning up after accreting matter, while others remain dormant? Is there a threshold of mass or angular momentum that flips the switch? What happens to the magnetic field as these objects spin faster? Is it buried, reduced, or somehow reconfigured into something more complex? Millisecond pulsars like black widows tend to have much weaker magnetic fields than their slower cousins. This is believed to be a result of the accretion process. The infalling material may bury the magnetic field, compressing or disorganizing it. But some black widows show surprisingly active magnetic behavior, especially in X-rays, suggesting the field may persist in strange configurations or reemerge over time. Could this lead to recycled magnetars? Could there be a stage where the field rebounds, creating bursts or flares before the system dies? These are not idle speculations. In recent years, a class of pulsars known as transitional millisecond pulsars has been discovered, systems that flip between accretion-powered X-ray states and rotation-powered radio states. One such object, PSR J1023+0038, has been observed flipping modes over the course of weeks or even days. It's as if the pulsar is deciding how to shine, by devouring matter or by simply spinning. This transitional phase may be common among black widow systems, as their companions lose mass and the accretion rate drops below a critical threshold. These transitions could tell us a great deal about the thresholds of astrophysical engines. What triggers a switch from one mode to another? What role does magnetic reconnection play? Could these systems erupt in bursts of radiation that we haven't yet properly identified, maybe even mistaken for fast radio bursts or other transient events? Speaking of which, fast radio bursts, FRBs, themselves might have a connection here. Some theorists speculate that certain types of millisecond pulsars, especially ones undergoing instability or interacting with dense plasma clouds, could emit FRB-like signals. The sudden release of magnetic energy, perhaps from a crust quake or magnetic reconnection, could lead to a short, ultra-bright pulse of radio energy. While most FRBs likely originate from magnetars, the line between neutron star types is increasingly blurred. Could a black widow undergoing a magnetic shift emit such a burst? Again, the edge cases open up new doors. And each time we think we've found the boundary, black widows reveal another layer of complexity. They aren't just destroying their companions, they're evolving themselves, changing spin rate, field structure, and emission profile. They are active players in their own metamorphosis, not passive inputs. There's also an emotional dimension to these systems. Consider what they represent metaphorically, a massive object whose only purpose is to take. It takes mass, angular momentum, energy, and eventually, the identity of its companion. And yet, in doing so, it reveals the deepest truths of the universe. It's a cosmic tragedy, but also a form of creation. The death of the companion gives rise to data, information we could not acquire in any other way. And what of the long-term future? If the universe expands forever, and stars stop forming, and black holes evaporate in a distant epoch, could black widow pulsars, or their descendants, be the last luminous objects in the cosmos? Spinning alone, slowly slowing, radiating their final pulses into an emptying sky. It's possible. Some theorists suggest that isolated millisecond pulsars, unimpeded by strong magnetic braking, could spin for trillions of years before slowing down significantly. Their energy output would decline, yes, but not disappear. They would be like the embers of stellar evolution, dim, ancient, but still whispering across the void. In a universe headed toward darkness, That whisper might be the last voice we hear. And in that whisper, encoded within each rotation of a Black Widow pulsar, lies a timeline stretching from the turbulent birth of a neutron star to the slow fade into cosmic silence. Each pulse is a heartbeat of a dying star system, a pulse that doesn't just signal rotation, but memory. The memory of a companion once vibrant, now evaporated. The memory of angular momentum passed like inheritance. The memory of violence, accretion, ablation, and the irreversible transformation that followed. To fully appreciate just how alien these systems are, let's step back for a moment and consider their scale, not in kilometers or masses, but in relative dynamics. A typical Black Widow system might have a pulsar with a mass of around 1.4 to 2.0 solar masses, compressed into a city-sized sphere, with a companion star whose mass is as low as 0.01 solar masses, or even less. Some have been recorded with masses of only a few Jupiter masses, skirting the boundary between star and planet. Yet this minuscule companion can orbit its massive partner in just a few hours. Imagine Earth orbiting the Sun not in 365 days, but in under 4 hours. The speeds are unfathomable. The gravitational interactions are relentless. The tidal forces in such a system are extreme. The companion is constantly stretched, distorted, and reshaped by the pulsar's immense gravity. The side facing the pulsar is bombarded by a relentless wind of relativistic particles and high-energy radiation. The companion heats unevenly, becoming an asymmetric object, bloated, irradiated, and often covered in hot spots that shift and flare with time. These effects are not mere curiosities. They change how the system evolves. The mass lost from the companion is not symmetrical. The shape of its orbit warps over time. In some cases, material streams into a faint disk around the pulsar, contributing to further angular momentum transfer. And then there's the plasma. In many Black Widow systems, the space between the pulsar and its companion isn't empty. It's filled with a dense cloud of charged particles, often stripped directly from the companion's atmosphere. This plasma can eclipse the pulsar's radio emission, causing the characteristic disappearances seen in timing data. These eclipses aren't smooth. They fluctuate, flicker, and sometimes create secondary peaks and troughs in the observed pulse profile. By studying these anomalies, researchers can map the plasma environment in real time, learning not just about the stellar wind, but about how charged particles move through strong magnetic fields under intense radiation pressure. This has led to another surprising role for Black Widow pulsars, as probes of fundamental plasma physics. The environments in these systems are like natural particle accelerators, comparable in many ways to the conditions inside fusion experiments on Earth, or even early moments of the universe itself. Here, we can see how magnetic field shape particle flows, how reconnection events create bursts of energy, how matter and antimatter may interact in ultra-relativistic jets. It's a physics lab we couldn't dream of building, yet it already exists, scattered throughout the galaxy, awaiting observation. There's also the broader role that Black Widow pulsars play in galactic ecology. They are often found in the dense cores of globular clusters, ancient spherical collections of stars bound tightly by gravity. These clusters are rich in millisecond pulsars, many of which may have gone through a Black Widow or Redback phase at some point in their history. Why do these environments favor such extreme binaries? One reason is stellar crowding. In the crowded center of a globular cluster, stars are constantly interacting, exchanging partners, colliding, or getting gravitationally flung into new orbits. A neutron star may capture a low-mass companion by chance, creating a new binary system where one never existed before. This opens another fascinating possibility. The life of a pulsar may not be linear. A neutron star might begin as an isolated remnant, enter into a binary later in life through stellar exchange, accrete mass, spin up into a millisecond pulsar, and then destroy its companion, becoming isolated again. It's a loop. A story of rebirth through destruction. And in this cycle, each phase leaves behind unique observational signatures. Some of these systems also produce high-energy gamma rays, likely from shock fronts formed where the pulsar wind slams into the evaporating material from the companion. These shocks can accelerate particles to near light speed, creating non-thermal emission that varies on orbital timescales. The Fermi Gamma Ray Space Telescope has catalogued several such sources, including the original Black Widow system, PSRB 1957+20. In fact, many new Black Widow candidates have been discovered by following up on unidentified Fermi Gamma Ray sources. What was once a mystery in the high-energy sky is increasingly being resolved into a swarm of devouring stars, spinning like buzz saws and devouring their mates. But we're still in the early days. Our catalogs of pulsars, though growing rapidly, are still far from complete. Especially in the southern hemisphere, many regions of the sky remain undersurveyed. As more sensitive radio arrays like Meerkat and the SKA come online, we expect to uncover not just more Black Widow pulsars, but entirely new classes of systems, some of which may challenge the very definitions we use today. Could there be pulsars with substellar companions even smaller than we've imagined? Could there be triple systems where a pulsar interacts with multiple low-mass stars? Could a Black Widow exist with a white dwarf remnant as its victim, having once devoured a main sequence star? The possibilities are endless. And each new discovery forces us to rewrite the story of stellar evolution, not as a fixed narrative, but as a branching tree, full of strange forks, dead ends, and loops. It also reminds us that even in destruction, the universe is efficient. No mass is wasted. No spin is idle. No radiation goes unused. Everything is repurposed, redirected, reabsorbed into the ever-unfolding story of matter and energy. And so we return to the metaphor. The Black Widow, spinning silently, devouring the last bits of her companion, is not just a monster. She is a teacher. A cosmic instrument tuned to the deepest resonances of physics. A warning and a wonder. And she reminds us that even in the darkest corners of the universe, there is structure, and from that structure, insight. Perhaps the most awe-inspiring thing about Black Widow pulsars isn't their violence, or even their precision, but their persistence. Long after their companions are gone. Long after their fuel is spent. Long after our own sun has flickered out and our galaxy has merged into something unrecognizable, they will still be spinning. Still pulsing. Still marking time. Their signals will stretch across an ever-expanding void, carrying with them the story of creation, destruction, and everything in between. In contemplating the future of Black Widow pulsars, we find ourselves peering not just into the arc of stellar evolution, but into the fate of information itself. Every pulse they emit is not merely radiation, it's a data point, a timestamp, a ciphered message from deep time. One could say that long after civilizations fade, long after planets crumble, the universe itself may still be readable through the persistent ticking of these remnants. In this way, Black Widow pulsars are more than just stars. They are cosmic archivists, encoding the tale of two intertwined lives, one predator, one prey. And their existence is not without philosophical implications. These pulsars embody a brutal kind of natural selection. They are the culmination of a survival mechanism driven by angular momentum and gravity. Their choice, to consume their companions, is not malicious, but inevitable, driven by physical laws and energetic optimization. Yet the result is eerily poetic. They spin faster, beam harder, live longer, and leave behind only the faintest vapor of what once was a full-fledged star. If there is any conscious metaphor to take from them, it is this: the universe preserves what endures, and it does so by forcing transformation through adversity. These systems also challenge our ideas about the boundaries of life and death in astrophysics. A star dies, becoming a neutron star. That seems like a clear end. But then, through interaction with a binary companion, it is reborn, spun up, recharged, made into a beacon once more. That death, then, was not the end, but a middle chapter. Likewise, the companion, seemingly destined to burn quietly for billions of years, is instead thrust into a hostile, irradiated environment, reshaped by pressure and plasma until it loses nearly everything. The dynamic of life and death here is not linear, it's cyclical and interactive. Stars do not die alone, they evolve through relationships, and those relationships can be violent, parasitic, or symbiotic. Let us return to the sheer physicality of a Black Widow pulsar system. A neutron star rotating 600 times per second has surface velocities near 0.2 times the speed of light. That's roughly 60,000 kilometers per second. On that surface, the crust is believed to be the strongest material known in the universe, tens of billions of times stronger than steel. Beneath it, a neutron-rich ocean. And below that, a core where quarks may roam freely, unconstrained by nuclear binding. The physics of this structure is alien beyond comprehension, and yet observable, indirectly, from Earth. Timing variations in their pulses, down to microseconds, can be measured and mapped. These fluctuations can reveal starquakes, glitches in rotation, or gravitational waves from orbiting bodies. Some Black Widow systems have even been proposed as potential hosts for planetary debris, tiny planets or asteroid-like objects trapped in the gravitational tug-of-war between pulsar and wind. These objects might periodically eclipse the beam or introduce subtle gravitational tugs in the timing signal. They could be the remnants of earlier companions, partially devoured and broken apart. Here, too, lies another mystery: what happens to the remains of the companion? In some cases, it's completely evaporated, leaving behind an isolated millisecond pulsar. But in others, a tiny remnant persists, perhaps no more than a few times the mass of Jupiter. These remnants are often superheated, irregular, and radiating heavily. They no longer resemble stars. In fact, it's hard to categorize them. They are ghost stars, victims of stellar vampirism, and possibly destined to shrink below the threshold of detection, becoming cosmic ghosts, objects we know must exist, but which we cannot yet see. As detection methods improve, we may begin to find more of these ghosts. The Vera Rubin Observatory, for example, will survey the sky with unprecedented depth and frequency, potentially catching rare transients and faint stellar remnants in real time. Likewise, gravitational wave detectors like LIGO, Virgo, and the upcoming LISA mission may one day capture ripples caused by tight, rapidly evolving pulsar binaries, providing a new way to study black widows and their kin without relying solely on electromagnetic signals. There is even a speculative frontier here. Could some of these systems evolve into black holes? If a neutron star accretes too much mass, beyond the Tolman, Oppenheimer, Volkoff limit, roughly 2.1 to 2.3 solar masses, it could collapse into a black hole. A Black Widow pulsar actively accreting from a small but dense companion may be on such a trajectory, especially if the accretion is sudden or violent. Observing such a transformation would be a once-in-a-lifetime event, a real-time glimpse of a neutron star crossing the boundary into a black hole, an event horizon forming amid a collapsing pulse profile. What would that look like? The pulsar's timing would become erratic, perhaps accompanied by high-energy flares as magnetic field lines snap and reconnect. The radio beam might falter, flicker, and then vanish. X-rays would spike. The gravitational signature would change. And then silence. The beacon gone. The pulse forever extinguished. Such a death would be final. But it would also be informative. By tracking the precise mass at which a pulsar disappears, we could more tightly constrain the limits of matter. We could determine how neutron degeneracy pressure behaves under extreme compression. We could finally nail down the elusive boundary between neutron stars and black holes, not theoretically, but observationally. And that, again, is the enduring legacy of these systems. They don't merely exist for our curiosity. They exist because the universe allows it. And in their extreme parameters, they reveal the underlying fabric of everything, from matter to space, from time to energy, from death to rebirth. As we listen to the pulses, counting each rotation, logging each eclipse, mapping each fluctuation, we are not just tracking objects. We are reading a story billions of years in the making. We are deciphering the mechanisms by which stars communicate with the void, and with us. And perhaps most humbling of all, we are reminded that these beacons, these destroyers, these keepers of cosmic clocks, will outlive us. They will continue long after our machines stop listening, long after our languages are forgotten, long after Earth itself is a memory. They are the universe's final librarians. And they are still writing. Even as we continue to tune into the steady, relentless rhythm of Black Widow pulsars, it becomes clear that these cosmic phenomena are not just destructive marvels. They are also creative in the information they produce. The pulses, eclipses, and variations they generate are more than just signals. They are a language of the stars, a syntax of physics and time written in energy and shaped by the laws that govern the universe. And like any language, the more we understand it, the more we realize what we still don't know. One of the most tantalizing aspects of this language is its connection to time itself. Pulsars, particularly millisecond pulsars like those in Black Widow systems, are among the most precise natural clocks ever discovered. Their rotational consistency rivals, and in some cases exceeds, the stability of atomic clocks. This property isn't just scientifically fascinating, it's functionally useful. Pulsar timing arrays are now being deployed as a kind of galactic-scale gravitational wave observatory. By measuring the slight changes in pulse arrival times across a network of pulsars, scientists can detect the ripples in spacetime caused by massive objects like merging supermassive black holes. This means Black Widow pulsars, despite their violent origins, are becoming instrumental in mapping the invisible structure of the cosmos. Their destructive power paradoxically contributes to our constructive understanding of fundamental physics. They may even help reveal the long-sought gravitational wave background, a low-frequency hum produced by cosmic events too massive and too distant to be detected by LIGO or Virgo. In this way, these dark and violent systems act as lighthouses for a kind of celestial sonar, helping us hear the slow song of the universe. In addition to acting as natural observatories, Black Widow pulsars also serve as cautionary examples of extreme limits in binary evolution. The radiation and particle winds that flow from the pulsar act like a jet engine directed at its partner. If this ablation is not uniform, or if the orbit decays too quickly, the companion can spiral inward catastrophically. In such cases, the companion may not just be evaporated, it may be crushed and assimilated into the pulsar in a single event, producing a rapid, chaotic increase in mass and a sudden alteration in the pulsar's characteristics. We may have already observed such a transformation. In a few recorded instances, astronomers have noted sudden disappearances of millisecond pulsars previously accompanied by low-mass companions, with no sign of the secondary star remaining. Were these silent assimilations? Did the pulsar consume its partner whole, passing a threshold that rendered it no longer visible to us in the same way? These are open questions, and they continue to blur the line between prediction and mystery. Then there are the systems that don't fit the mold, the so-called Redbacks, which are similar to Black Widows but have larger companions and more chaotic, reversible mass transfer. Some Redback systems seem to oscillate between accretion-powered X-ray states and rotation-powered radio pulsar states. This back-and-forth switching behavior shows that these pulsars can change roles depending on how much material they are receiving at any given time. It's as if they were masks, one moment a quiet radio lighthouse, the next a blinding X-ray emitter, then back again. These transitional millisecond pulsars add even more nuance to the evolutionary paths we try to map. In many ways, they may be the missing link, pulsars caught in the act of becoming Black Widows or returning from that phase entirely. What complicates this even further is the role of magnetic fields. A pulsar's magnetic field is thought to decay over time, but interactions with the companion star can temporarily remagnetize the neutron star or alter the alignment of its magnetic poles. This changes not only the character of the emissions, but potentially the detectability of the pulsar itself. A misaligned magnetic field could produce pulses that never cross Earth's line of sight, making the system effectively invisible to us even if it's active. In this way, the true number of Black Widow pulsars may be far higher than current observations suggest. It is here that technology becomes our ally. As new telescopes come online, both ground-based and space-based, the sensitivity to faint signals, irregular eclipses, and intermittent pulse profiles will improve dramatically. Projects like the Square Kilometer Array, SKA, are expected to uncover thousands of new pulsars, some of which will almost certainly belong to exotic subclasses of Black Widow systems. What we see now may be only the tip of an enormous and complex iceberg, a hint at a far richer ecosystem of stellar cannibalism, rotational extremes, and plasma interactions. And beyond even that lies the frontier of theory, where mathematics and simulation attempt to model these systems with ever-increasing fidelity. 3D magnetohydrodynamic models now try to replicate the pulsar wind interactions with companion outflows, mapping shock fronts, relativistic jets, and electromagnetic reconnection events. These simulations don't just confirm observations, they predict new phenomena. For example, they suggest that in some cases, the pulsar wind may create a secondary torus of material around the entire binary system, adding additional scattering layers and contributing to the observed variability in pulse arrival times. Even more daring hypotheses speculate about gravitational lensing effects in tight binaries, where the neutron star's intense gravity can bend the light from its companion in subtle but measurable ways. As our precision increases, it might become possible to detect these microlensing events and use them to map the mass distribution of both stars in exquisite detail. This would provide another indirect measure of the neutron star's mass, further constraining the equation of state for ultra-dense matter. The strange part is, in studying all of this, these exotic processes, these improbable systems, these barely comprehensible transformations, we're not just learning about space. We're learning about the limits of matter, the endurance of time, and the behavior of physical law under the most extreme conditions imaginable. We are learning, in a very real way, about what is possible in our universe. And yet, despite all this progress, a Black Widow Pulsar remains, at its core, a mystery. Its very name evokes unease, a warning, a story of silent violence. It is a system that unravels its own partner molecule by molecule, without ever making a sound. It is an emissary of entropy and order in equal measure. And in that contradiction lies its true power. It is both destroyer and archivist, both executioner and historian. It ends what it touches, but preserves its memory in each beat of its pulse. And we, the listeners across space and time, must choose what to do with that memory. In the grand scheme of cosmic storytelling, few tales rival the haunting narrative of the Black Widow Pulsar, one of quiet annihilation, of orbits becoming cages, and of life transformed into debris by the sheer will of gravity and magnetism. But the more deeply we peer into these systems, the more we begin to appreciate their paradoxical beauty, the elegance of physics playing out in its rawest form, stripped of any comforting familiarity. The violence of the Black Widow Pulsar is not random, it's sculpted by rules. Consider again the balance of forces at play, the relentless radiation pressure from the pulsar's wind versus the tenuous gravity holding the companion star together. This dance is exquisitely sensitive. A slight increase in accretion can amplify the pulsar's rotational energy and magnetic field, which in turn intensifies the particle wind and accelerates the mass loss from the companion. It's a positive feedback loop spiraling toward collapse. In the final stages, the companion is often reduced to less than 0.05 solar masses, a ghostly shell of its former self, nearly transparent and swathed in the very energy that is erasing it. We must also look at the astonishing time scales involved. A typical pulsar might take millions of years to spin up via accretion from a companion. During this time, the pulsar and companion orbit each other thousands, even millions of times. Each orbit shaves mass off the companion like a slow-motion guillotine, trimming away at a star while tightening the noose of gravity. By the time we detect the system, it has already undergone epochs of transformation, most of them invisible to our instruments. We are catching the final act, the closing scene of a tragedy written in radiation. And yet, some of these systems refuse to end quietly. The sheer energy involved in the evaporation process can occasionally cause massive outbursts of gamma rays, radio flares, or even optical brightness increases. These eruptions are believed to occur when dense pockets of gas, stripped from the companion, are suddenly accelerated or heated by the pulsar wind. In rare cases, the magnetic fields can tangle and snap, producing short-lived jets of relativistic particles. These flares, like cosmic screams, hint at the chaotic process underway. Astronomers now suspect that some fast radio bursts, FRBs, those mysterious, millisecond-long radio pulses detected across the universe, might originate from systems like these. Although magnet-ars remain the leading candidates for FRBs, a subset of them, especially the repeating ones, might be tied to exotic binary pulsar interactions, including those in Black Widow-like configurations. If this link is confirmed, it would provide a stunning new avenue for using Black Widow pulsars as tools to probe not just our galaxy, but intergalactic space. Their pulses, bent and delayed by interstellar gas and magnetic fields, act like tracer bullets through the invisible matter of the universe. But let's step back to consider something even deeper: the implications of their sheer existence. These systems shouldn't be common. The precise conditions needed to form a Black Widow pulsar, having a neutron star in a tight binary with a low-mass companion, evolving in such a way that accretion occurs without immediate merger, are rare. Yet we found dozens. And the more we look, the more we discover. This suggests either that our models are missing something or that nature finds more creative ways to form these configurations than we currently understand. There's even the possibility that many of these systems are hidden from us, not by distance, but by orientation. If the beam of radiation emitted by the pulsar is not directed toward Earth, we wouldn't detect it as a pulsar at all. Similarly, if the companion's outflow is thick enough to absorb or scatter radio signals, it can cloak the entire system in plasma fog, making detection nearly impossible. These, invisible, Black Widow pulsars could be silently annihilating their companions across the galaxy, just beyond the edge of our current sensitivity. This leads to an eerie realization: the number of Black Widow pulsars we observe may only be a fraction of those that actually exist. Statistically speaking, for every one we see, there could be dozens we don't. The Milky Way could be riddled with these systems, hidden predators whose only trace is the occasional flicker of disturbed light, the unexplained drift in a stellar orbit, or a tiny, ghostly object where once a star shone brightly. And what of the final state? Once the companion is completely consumed, what remains is an isolated millisecond pulsar, one of the fastest rotating, most stable beacons in the cosmos. These solitary remnants are often assumed to be harmless. But the memory of their past lives lingers. Their rotation rates, magnetic alignment, and even their internal structures bear the scars of the long devouring process. They are no longer normal neutron stars. They are hybridized survivors, reforged in the crucible of binary warfare. Some astrophysicists have begun to wonder whether such pulsars, given their altered internal dynamics, might be more likely to undergo exotic phase transitions, perhaps transforming their cores into quark matter, strange matter, or other hypothetical ultradense phases. If so, these Black Widow survivors might one day undergo catastrophic events, collapsing into black holes or detonating in rare stellar quakes powerful enough to emit gamma-ray bursts. It's a theory still in its infancy, but it underscores the point: these systems are not static. They are active, volatile, and in some cases, potentially unstable. And here, again, we return to the philosophical implications. A Black Widow pulsar is not just a star, it is an endpoint, a monument to transformation. It is the product of chaos, sculpted by physics, sustained by violence, and destined for lonely brilliance. It teaches us that even the smallest objects can exert enormous influence, that partnerships can lead to annihilation, and that time reshapes everything, often in ways we cannot predict. It's also a reminder of our limitations. For all our telescopes and simulations, we are still spectators on the edge of an abyss, watching ancient mechanisms unfold, trying to reverse engineer their logic. We build models, gather data, and make predictions, but the universe always finds new ways to surprise us. In the case of Black Widow pulsars, the surprise is that such horror can be so orderly, such violence so rhythmic, such destruction so mathematically elegant. And perhaps the most haunting thought of all is this: there could be a Black Widow pulsar lurking right now in our galactic neighborhood, its pulses too faint or too misaligned to detect, silently devouring a companion star in the dark. Its story unfolding unnoticed in the background hum of the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.